Check 1, 2.
Check 1, 2. Check. Mic 5, check 1, 2, check. I was a little low in the room, or is it just me? Give me a thumbs up, I can have one. Check. Mic number 5, check. Mic 5, check. 1, 2, check. Check. Podium mic, check. Sounds good, okay. Panelist table, check. 1, 2. Check. 1, 2, check. Check. Check 1, 2, 3, check. Mic number 6. Mic 3, check. One, 2, 3, check. Sounds a little low. Check. 1, 2, 3, check. 1, 2, 3, check. That was good. Good in the room. Okay.
Small businesses, telephone communication is still a kind of groping in the dark. Hello. Who's this? But now you can overcome all that with the Merlin system from AT&T. It's incredibly easy to use. So if your business isn't running as smoothly as you'd like, say hello to the Merlin system and put an end to AT&T, the right choice. business is running as smoothly as we want. Sail over the moon system. Now you can overcome it with the moon system from AT&T. It's incredibly easy to use.
to be able to.
What target are you? Yeah, I suppose it's probably doesn't need to go here.
Any questions so far?
all asking the same question.
Check, check. Just a quick tech check. Those joining us remotely, can you hear us? And if you're able to, please unmute and you can speak into the room.
Hello, hi, it's Maggie.
Yep, we can hear you. Thank you.
Of course.
All right, so we are at 9. So I'll just say this for people who may still be outside. We'll get started in maybe a minute. And if you're virtual, maybe finish wrapping up making your coffee or tea or whatever, and yeah, we'll get started in just a minute. All right, so it looks like we have, I think, everybody that we need to get going this morning. So first off, welcome. Thanks for joining us for the 2024 Improving Scientific Software Conference. I know definitely I've seen some of you in past years, and hopefully we have some first-time attendees as well. So my name is Brian Vanderwind. I am a member of the ISS Chairing Committee, and I'd like to just give a quick shout out to the rest of the folks that are on the committee. I won't ask them to stand up because probably some of them are in meetings and things like that, but they'll be here throughout the week. And obviously this couldn't have happened without their efforts. And it especially couldn't have happened without the efforts of Tasia Peterson, who I will have wave in the back of the room there. So thanks, Tasia, for all that you do. She really you know, again, so many of the logistics would not have gotten done without her diligent efforts. And, you know, she just had a baby last year, so managed to get all this done while, you know, being a new mom. So that's awesome. And also thanks to Multimedia Services for the work that you do throughout the week and, you know, making this all happen as well. So appreciate everybody, and obviously appreciate you all for joining. So just a couple of quick housekeeping notes, and then we'll get into a keynote panel. So first off, we have 4 days this year, I guess 3.5 sort of. The Thursday is a bit abbreviated. So we've grown a little bit since last year, which I think was great, and we hope to keep that trajectory going. And I think, you know, if you like the theme of the conference but haven't submitted before, and you might consider doing that next year, I'd highly encourage it. You know, we have a pretty, I think, relaxed atmosphere here, but it's, you know, people who are sort of in a community of practice around improving scientific software. Also just want to remind folks that when you registered, you agreed to the NCAR Code of Conduct. So we just asked, obviously, that you adhere to that. Should be pretty self-explanatory, but if you have any questions about that, certainly reach out to any, either, you know, Tasia or I or anybody else that you see who sort of seems to be in an official capacity. And then in terms of, you know, the logistics of each day, so there's a lunch each day, and then there's snacks twice a day, except for Thursday. I think we have one snack break because it's a shorter day. I believe coffee and tea and all that good stuff is available pretty much all the time. So feel free to, you know, fuel up whenever you need. And I think that's everything that needs to be said. So I guess without further ado, I think we can have our 3 in-person panelists come up here to the stage. Feel free. And we have 5 chairs there, so feel free to take your favorite. And you know, if any of you haven't used this setup before, basically the mics there, if you press them, you just hold them, and then the mic is hot. So if you take your finger off, it's going to cut you off. But otherwise, it should be pretty self-explanatory. And then we also have Helen, who's virtual, and I believe we've done a sound check and everything there. So we should be pretty good to go. Okay, so what we decided to do this year for opening up the conference is to do just a general keynote panel. The topic is sort of just the general theme of this conference and the spirit of this conference. So we want to talk about experiences with modernizing either, you know, scientific code bases or the teams that work on scientific code. Specifically talking about like sort of the challenges that have been encountered and also the opportunities that people have found when they're trying to engage in these types of activities. So the structure of the panel is, so we have our 4 panelists, give them each an opportunity, about 5-ish minutes, to introduce themselves and speak a little bit about their, you know, the reason why they're here today. And then we'll go into basically just an open Q&A. I'll probably start us off with just a question to get the discussion going. But after that, anybody who's encouraged to ask a question of our panel, feel free to go up to the mic, and they should be live. So yeah, feel free to just line up if you have a question, and we can get the conversation going. And we'll do that for about an hour and then have a break and then go into talks. So our 4 panelists for this session, we have Alex Richert there. We have Alicia Karsbeck. We have Thomas Hauser. And then virtually we have Helen Kershaw. So appreciate you all joining us. And I'll just, I'll ask Alex to start us off. And yeah, I believe so. Multimedia, we have. Excellent.
All right, thank you. Good morning. My name is Alex Richert. I work for Redline Performance Solutions, and for a few years I've been working with the National Weather Service on a number of contracts, for a while on the operational side, and currently on the NCEP Libraries team under the Environmental Modeling Center. Next slide, please. So one of the key challenges that we face with code modernization is that a lot of our code is quite old. For preparing for this, I went back through some of our libraries and model code, and we've got some subroutines going back to the early to mid 1970s. We've certainly got a lot from the 1980s, some from the 90s, which doesn't feel like a long time ago, but that is about 3 decades ago. To make this situation a little more challenging, a lot of the original developers have, retired, changed jobs, passed away, et cetera. And a lot of it is not particularly well documented, and this creates a challenge for us. One thing that I think is somewhat unique about our situation and our approach to software modernization is the fact that not only are we responsible for the scientific advancement of our models, but we're also responsible for operational stability. I have a colleague at EMC who likes to point out that we're trying to build and fix and renovate our car as we're driving the car. So we can't just sort of pull our car over at the side of the road and leave it there and just go get a new one or start all over. So we can't, even if it were technically feasible, we can't just rewrite the operational suite and modernize everything. So we have to be strategic about how we modernize things, and we have to be systematic. And it's really that systematic part that I want to focus on. So next slide, please. So to give a kind of overview of what we're working with on the libraries team, here's our software stack. I won't read through all of this, but I'll call out a few items here. Over the last maybe 5, give or take, years, we've moved all of our codes over to CMake, so that's been a pretty big advance. We've got all of our codes working equally well with the compilers that we need to support, and we are about 99% of the way to Intel One API support, which will eventually become necessary for operations. For documentation, we used Oxygen for all of our compiled code, so that lets us integrate our documentation into the compiled code itself, but also have a nice HTML-based product, which is nice for developers. For our continuous integration, building and testing, we use GitHub Actions. I want to specifically point out that we do required code reviews for all of our code changes, and we also have required unit tests. So that's something we bake into our repository settings, because we want each of our code changes to not introduce any bugs or regressions, of course, and we want to make sure that all of our code changes adhere to certain standards, because we generally take the position that it's better to go to the extra effort of changing something now and making everything work than sort of kicking the can down the road, fixing bugs later, and so on. So I would argue that really the 2 most important pieces of retaining institutional knowledge and making ourselves resilient against the developers who retire and change jobs and so on are automation and documentation. So I think that's a really key part of what we do. Next slide, please. So again, I think we take a systems-oriented approach where we try to put systems in place that will make things as easy as possible for ourselves in the future, and that'll pay off down the road. So some of that is our package management infrastructure, and I'll talk about that more in my talk on spack-stack later. And then again, automating our unit testing, requiring unit testing for all new code contributions, as well as documentation. Please don't miss Ed's talk on Doxygen on Wednesday. And on top of our technical systems that we put in place, we also take the view that every developer is responsible for the health of our code. I think there can be a sense among developers, especially people with scientific backgrounds like myself, who maybe are not trained software engineers. There can be a sense of, okay, I just want to push in my one fix, my one monkey patch, and then, I'll leave it to the real developers to worry about the rest later. But we find that the overall health of our code really benefits when every developer is considered responsible for testing, documentation, and of course, the overall health and stability of the code. So I'll leave it there, and I look forward to the rest of our discussion.
All right, thanks, Alex. Alicia, why don't we move on to you?
So hi, everyone. My name is Alicia Karspeck. I want to just spend a few moments just telling you about my background and how I came to this panel. I spent most of my academic career at the National Center for Atmospheric Research at NCAR, in CGD in the ocean section there. So I know quite a few people here from that time of my life. Helen, I worked closely with, which was amazing. So I worked on both decadal prediction and data assimilation. So I'm not trained as a software engineer, but through the work working basically as a scientist at NCAR, doing modeling and data assimilation, I was very sort of involved in a lot of the software engineering efforts that were going on. They're very key to the success of the science at NCAR, obviously. I actually left NCAR in 2017 to join the private sector. And I've been, for the last 6 years or so, have been in sort of a number of different positions within the private sector where we are actually using scientific software for either commercial applications or for applications that are sometimes in the nonprofit space, but are sort of outside of the traditional research environment as we're used to thinking of them. Where I am currently actually is I'm a co-founder and the CTO of a nonprofit R&D organization. We're here in Boulder called Seaworthy. And what we do is we work on the problem of making available the right scientific software for folks within the ocean-based carbon dioxide removal industry. So there's a little niche in there. So the codes, for example, that are needed by this sector of kind of this emerging private sector are ocean and biogeochemical models of the sort that are developed at places like NCAR and at academic institutions. In my previous roles at other commercial enterprises, we were using codes like WRF and other coastal ocean models that are developed within the scientific enterprise and the academic enterprise, but sort of pointing them towards things that are existing within the commercial sector. So that's kind of my history of getting here. And one of the themes that I want to talk a bit about in this panel, there's a lot of different things we could focus on in terms of how to improve scientific software. But one of the themes I want to highlight is this concept that so much of the code that's being built within, again, at national labs and at federally funded labs and also in academics, ends up being really, really important for folks within the private sector. And a lot of those groups who are using those codes tend to be startup organizations, which have actually very, very lean internal software engineering teams themselves. And they're very much relying on the use of this software that has been developed in the public as a sort of a source for their own commercialization. Again, the concept there is that things remain open source, but people are sort of building products around that. So again, one of the themes here I want to talk about is actually the use of scientific code by non-scientists and what that actually looks like in terms of the types of teams that we build and the types of challenges that we have in that space. So a couple I want to mention. One of the really positive things that I see that comes out of this is the use of these codes within the private sector actually leads to a lot of different types of testing of the way that these codes are used. So my observation as from being a scientist is that very often there are relatively few people using the codes in the same ways over and over again. It really works for their research applications, or the codes are being used in operational systems where, again, they're being sort of exercised along very similar lines. One thing you see if you sort of branch out into the use of these codes within the private sector is a lot of more diversity in the types of use cases. The result of that is a lot of exposure of sort of bugs within the code that would have otherwise never been exposed because they're being used in sort of novel ways. So one of the challenges there is how does that information that's being kind of developed outside of the academic space and out of the traditional developer environment get pushed back into making more robust code overall? Who pays for that? There's obviously serious costs associated with that in terms of software engineering expertise, in terms of developing that. And what is the appetite for folks who are within sort of the science space for incorporating and encouraging the use of these tools within the private sector? So one theme that I think is kind of an interesting one there. I'm happy to explore that offline as well. Another one is this concept that I'd like to kind of bring up of the idea of folks who work in this space called product. And for anyone who's ever worked much in the private sector, there's this concept of sort of the development of a product that's around and oftentimes a software system. And the role of that sort of product function is to think about how the actual use cases and the utility of this software and to really make the connection between users and the software itself. And there's a lot of interesting, I would say, ways in which the scientific community, academic community could maybe adopt some of that thinking around having very specific, I would say, functions in terms of the staff whose job it is to understand who are the real users of this software and is it really being built for them, and sort of really consistently thinking about that. So again, like this whole concept of the modernization, I really think a big theme here is to really think broadly about how these codes are used outside of just the public sector, and to think about, what does it mean in terms of the way that we build those teams to support that. So I have a lot more I could say, especially about things like data accessibility and things like that, but happy to take that in questions. Thank you.
Thanks, Alicia. Why don't we continue down the table here? Thomas, go ahead.
Yeah, good morning, everyone. I'm Thomas Hauser. I'm the director of the Computational Information Systems Lab at NSF NCAR. I actually liked what I just heard from both, right? I mean, our software is kind of old, has grown, and the team building. So I hired actually a product owner for our cloud and for our data commons. So I think it's interesting. One of my biggest concerns is that our software and the computing trends, it's a really big challenge, right? There are disruptions in multiple dimensions. I mean, our double precision floating point performance of our computers is not going to get faster. And all the investments right now are in AI hardware, right? How do we make use of AI hardware so our software runs well on that? And that's a challenge if you have millions of lines of code. There's another disruption. I think our users, I mean, I was at the SPAD workshop. They want ease of use, right? They want to take our code, and I think maybe that's also in the startup. They want to take our code, easily port it to another platform, and also modify it, right? So how do they modify maybe physics aspects there? The other disruption, and again, I don't have good answers right now. We have a concept we developed, is AI. I mean, implementing that in our codes, replacing some of our physical parameterization. I mean, I think in the weather world, I mean, there are prediction software now that do AI, they just based on machine learning and data. And then on the same way, our model complexity is increasing, right? We want aerosols, we want additional physics, we want everything basically in our model, complex land, and then higher resolution. I mean, that's what I heard really out of the SPAD workshop. How do we do this with kind of a hardware trend that really is not helping us? And then integrating our models in really complex workflows where we take data from satellites and combine that with our model work. So one of the things I've been working on as part of a computational science strategy at NCAR is kind of treating our models as scientific instruments. I mean, that's really, we want to change the conversation with our funders too. You can't just do what we have been doing and treating that as a scientific instrument. I mean, this is the concept what we call community software facility. This helps us maybe to rethink how do we develop and support our models. How do we do better support across NSF NCAR, right? I mean, one of the things I clearly heard in this workshop, NCAR is big and distributed, we do a lot of things, and then new people that want to engage with us really don't know how to engage. So I think having this more centralized, how do we do, we can do co-design with our computational facility. How do we bring in new technologies, domain-specific abstractions? I mean, I was part of a DOE project that used a very old Fortran code. It was slow. And we moved it to AMRX, kind of a domain-specific abstraction, and imported it. And at the end, we had really a fast code. How can we do that here? Verification is another challenge, right? Moving from platform to platform, this can't be bitwise. And then how do we democratize access to our models? I think that ties a little bit with Alicia there. Science gateway clouds? How does this all fit together? And I think the big question for us, right? I mean, we are a science organization, so how do we invest in software engineering? I think that's one of the challenges. Every time if there's a new initiative, oh, it's all about the science, and then I'm here and asking, what about the others, the software engineers, the consultants there? The other question, what can we do? What can we stop doing? Can we outsource things? Can we use things there? And I think we've come a long way over the last few years. There's the SEAL team, the software engineering across the labs, that has really come together and put some really nice recommendations. I want to just highlight a few. I mean, code quality matters. I think that's part of really unified testing. Software engineers need more influence in planning these projects. I think we have made some progress with CIMA. There's now 4 software engineers plus 4 scientists leading this project, but there's a long way to go. We need to provide new and better ways of user support. I think that's another one area. And then we need to allow time for workforce development. I mean, this is one of the challenges, right? You rush from project to project to project. How do you really learn new things? And this needs support, I mean, from the top, I think, to make sure the SEs have the time for that. So that's all. And I'm very curious. I think there's a lot of themes that align here. So looking forward to your questions. And
Thanks, Thomas. And then, yeah, let's jump to our online participant, Helen. Why don't you go ahead and introduce yourself, and then we'll move on to the Q&A.
Hi, everyone. I'm Helen Kershaw. So I'm the lead software engineer for DART, which is the Direct Simulation Research Testbed here at NCAR. So I get to work with lots of cool people, including Alicia at one point. So we're totally open source, right? Open from design right through to code. We've got a large for scientific software community. And we've got sort of 20 years of development to maneuver, shepherd, hack, wrangle. So I call myself like the lead software engineer. I actually only have one person reports to me and 2 students. So a lot of my work involves working with people who don't report to me and have conflicting interests and incentives and things they want to get done with Dart. So yeah, so I guess I'm interested in how we develop that community code is kind of a beast really, and it's exciting and it's interesting to work at. But yeah, how we can I don't know, build communities and improve, I don't know, I guess general computational literacy, software engineering literacy as a community, to make better products overall.
All right, thanks, Helen. And thanks to everybody for doing your introductions. I guess since I didn't mention this earlier, I should ask, are we doing the Slido for remote participants who want to ask a question? Okay, excellent. So yeah, if you are attending virtually and you have a question for our panel, just put it in the Slido and we'll try to mix those in as well. I guess I had a bunch of questions, but I think probably some of our panelists might have questions for each other or just for conversation. So Alicia, I don't know, do you want to go ahead?
Okay. One of the things I wanted to point out, and again, I don't know who really the profile of everyone who's in the audience. I'm having this assumption that you guys are all scientific software engineers or data engineers who are somehow working within kind of the public enterprise. Like, is that likely is that the right profile?
I think roughly, yeah.
Yeah. So one thing I want to just reflect, which is, and I can't emphasize this enough. Okay, so there is a sense outside of the academic environment. I'm using the word sort of science and academic as shorthand for, because of course there is science that happens in the private sector as well. But kind of shorthand for, research, basically research focused, science focused. Usually it's in the public domain and otherwise in sort of the academic space. So that's kind of the shorthand I'm using here. The types of scientific codes that are developed within that space, and I'm including in that basically geophysical models, right, obviously, but also things like data assimilation systems, DART falls into this category, things that are built where the belief is that they are for research, okay? These types of codes are not really replaceable in the private sector for a number of reasons. So some of it has to do with just the sheer enormity and amount of functionality that already exists in these codes. So that's one we're sort of already familiar with that concept. But the other one has to do with a level of public trust in these sort of scientific codes that exist. So this gets back to kind of this issue of AI a bit, which is that, you know, the concept that a private company can come in and replace something like a geophysical code with like a sequence of just sort of black box AI is really not something that's realistic for a lot of science-based commercial problems. People who are in general, they rely on the concept that there is high amount of trust and integrity within the scientific community that's built into the way that these codes are used. So anyone who's in the commercial sector who's then relying on them is basically able to say, like, these are codes that are open, they're transparent, they're built by people who don't have sort of improper incentives. So I want to just make the case that how core it is for the success of the commercial sector to have a really thriving sort of software engineering model building activities that are happening within the scientific sector.
Thanks, Alicia. I guess, do any of our other panelists have any follow-up on that, or?
Yeah, I think I'm an engineer, so I started a mechanical engineer. So one of the differences coming into earth science versus engineering, right? In engineering, there are actually small software companies like Fluent or others that actually produce software that's used. And there's open source as well. I mean, I think what I've heard, companies, even big companies, use a mix. They trust the commercial code more, but then they use some open source codes to do the optimization because they can't afford the licensing cost. So it's an interesting difference, right? Why in engineering, maybe these software companies kind of, I mean, they are all fairly small, but sprung up versus maybe the earth sciences where you have more open source codes.
Oh, I just wanted to ask you from the kind of private sector perspective, what are the aspects outside of just kind of technical constraints? What are the aspects of this kind of open source, the science code that you're describing, that make you more inclined to trust or use one code? Or what are the things that we can be doing as the developers of those code to kind of help you out and make your development process easier?
Yeah, so I mean, the biggest thing will come as no surprise, which is the lowest friction code almost always wins. So, right, so the code that you want to use is code has a lot of publications behind it, right? So a great example of this is DESM, WRF. Like these are codes which have huge, you know, sort of a whole history of scientific uses, and then have been in some ways created in a way that's lower friction. And so, you know, a lot about when we think about like the best practices of software engineering, the whole sort of upswing in things like object orientation, putting things on the cloud, they all have the effect of making them lower friction, right? And that's really the core thing. Same with things like the data accessibility issue, which is, you know, almost all models and codes that we use have behind them some form of what I would call metadata, or, you know, data which allows the models to run, right? Making sure that data is accessible and usable is just as important as thinking about raw data sets, right? So again, I would focus on sort of the concept of the trust with the models and then the friction within the models. Can I just say one more thing and then I'll kind of quiet down a little bit? What Thomas said, which was around this issue about why it is that trust issue is so important in some industries and maybe less of an emphasis in others. The way that I would put that is that there are scientific codes, and I'll put numerical weather prediction codes in this category, where there is access to independent verification for the results of those codes. And when you can have independent verification for the results of a code, the issue around trust and credibility is not as important, obviously. So the thing with numerical weather prediction is you can actually observe the skill over someone's, you know, over a couple weeks and make comments about the actual validity of one code versus another. As soon as you start to think about problems like carbon dioxide removal, climate change, these types of like long-term risk characteristics like flooding and heat, there is no real way to verify the outcome of these codes. And as a result, you really rely then on the sort of the fact of there being a scientific integrity and a scientific body of work that's underpinning them. So that's what I think is a difference often between engineering codes and codes that are used in sort of the climate space and the climate adaptation space.
Can I have a question actually to the audience? I mean, one of the things I'm worried about on the use of our code, right? A company, I mean, nothing that doesn't really know what they are doing, downloading our code, compiling it, maybe turning on optimization. And then because again, our codes are, I mean, disturbances kind of get amplified in a non-linear way. And then producing results and saying, oh, this is coming out of CSM. And in reality, it really doesn't produce the correct results. And that could be even, I mean, I had a conversation with a researcher at this last workshop where she discovered that the simulation she did initially were just basically an amplification of some really small disturbance, and only through nudging she was getting the right result. So I'm curious about people doing the software. Are you worried about that, and how do we maybe prevent that?
And if anybody wants to apply to Thomas's question directly, feel free to go to a mic.
So my question is, somebody taking your software, I mean, our community models, and then doing something with it that isn't really right? That maybe compiling in a way that changes the climate if you do all the verification. I mean, are you worried about that at all? Or is that just the risk we take by providing a community model?
I think that's the risk and the benefit, right? It's kind of touching on what Alicia was talking about. Like, it's better for people to run your code, and if they find out you can twiddle these knobs and get something crazy, then that's something you want to know, right? But yeah, I think there's some trust in publishing, right? So when they go to publish a paper and someone reviews it, is that good enough to catch whether they've made some terrible decisions implementing the code? I don't know. But I don't think it's a bad thing for more people to use code.
My name is Ryan Cabell. I'm the lead developer for Wharf Hydro, and we have some of this happen. We get emails to our help desk, people who are clearly not really understanding what's going on and doing things wrong. But I think Helen kind of beat me to it. For the academic world, I'm less worried about that because of the publishing process. In the private sector, it's a bit Machiavellian, but if they get the wrong result and they sell it, then maybe they don't get another contract, right? I mean, we're trying to help them, and I want them to succeed. But, I have conflicting thoughts on where the responsibility is for the private sector versus sort of an academic community.
Yeah, I think that's something that kind of in general is a question that our committee was thinking about before this panel is, and this could be pertinent to private public engagement or public community engagement or anything like that. But I think, specifically, we've kind of been talking about the private public use of models and maybe feeding back developments into those codes and how that can work. So obviously there's just challenges in terms of communication from an engagement standpoint. And there's also funding challenges in terms of how that gets paid for. And you brought that up, Alicia. So I'm curious what our panel, what thoughts do you have in terms of, any sphere where you're worried about the engagement of the code that you're trying to maintain? What active planning do you put into that, and what sorts of things are you concerned about or even excited about? So I'll leave that open.
I mean, I think one partial answer to that is we concern ourselves with documentation a lot, and sort of partial answer is that we've tried to get away from, in terms of developing our codes, bug fixes, or even user assistance for that matter, trying to do things in a public space, namely through GitHub issues and this sort of thing, so that we're not having the same conversations over and over, and so that we can have other users benefit from what's there. So trying to get away from doing everything over email threads and this sort of thing, and trying to, encapsulate things into, GitHub discussions, this sort of thing. I think there's some value there in, people learning from the experiences of other users. So, yeah, trying to get as much information out there as we can, and lower that barrier to users getting acquainted with the codes and understanding the limitations and so on of the codes, getting back to Thomas's point.
Oh, and I should say, we also do have a one of those throwable mics. So if
Oh,
you
you can
prefer
throw-
that, feel free to raise your hand and we can
Hello?
we can bring a mic to you.
Hi, my name's Jim Edwards. I'm a CESM developer. Alicia, you've given high praise to open source software and the process that goes through, in the publication process and everything. But in your opening remarks, you said something about, finding a problem or some area of development that you might want to do in the private sector, and how would that be paid for? And I guess my question is, how can we get the private sector to recognize the incredible resource that's being given to them, and recognize that when they contribute to the model, they're only, making a payment in kind for something that they've received for free?
So a couple things is that I think a lot of companies do recognize that, and actually attempt to have those processes in place where they're feeding back into the open source codes. So, I think the question is how can you help them understand how important that is? And I would say if they don't already understand that, then they probably don't have a viable business model anyway. So people who are really serious about development in the private sector who are using these models, they are paying usually for some portion of the time of their software engineers to contribute back to open source code. That's what we do at Seaworthy, right? We have our software engineers who come out of the Pangeo community, which I'm sure many of you are familiar with. They have a certain amount of their time, something like 20%, which is actually meant for that sort of pushing back into the community. So I think that they do know, most of them do know that. Yeah.
I have a comment too. I mean, I've been thinking about this too at CU as well. I mean, are there ways where we as NCAR can say, we can provide additional service for cost to commercial entities that are beyond what we would do normally, right? Maybe more closely consulting and or development for that. But I think that's definitely challenging, because again, I think startups are probably not flush with cash in in this space, but maybe with some larger companies. I mean, in general, I think even as NCAR, right, we are a science organization, and software is really our instruments, right? That's why and hopefully as part of ABR, we're having some discussion. Can we do less science and more software engineering to modernize our software? But these are very, very difficult conversation in a science organization.
Oh, so Megan, just so stay there. But I think we do have one Slido question, so we'll do that and then we'll jump to yours.
This is just a quick comment from Gregory Lemieux. It says, I suspect that the generally high level of friction in using many of these codes is a common. Oh, sorry. Oh no. Let me start over. I suspect the generally high level of friction in using many of these codes is a common bulwark against misuse of code results. For instance, it requires a deep engagement with developers and existing users, as such potential users might not engage.
Thanks for the online comment. Megan, why don't you go ahead and then we'll sort of address both points.
Hello, my name is Negin Sobani. So I wanted to ask a question or bring up this point about the validity of the models when the settings are not like set up like correctly, because I think similar to any technologies that's out there, our models and our software can be used for different purposes. Similar to AI, that can be used for different things. Our models can be used for different things, and some of them are not correct, like scientifically correct. For example, WRF has like a ton of options and configurations that a lot of them might not end up in a correct result for that region. With some models, it's more like the user needs to know more about those settings to change it. It's kind of like it has like some prepackaged scientifically validated, like CESM, prepackaged scientifically validated cases, but something like that doesn't exist with WRF. So the user needs to read the literature on that region that they are running the simulation on. And my point is that it's for a lot of users, NWPs and climate models are also like a black box, similar to AI, because, and that was a question that someone asked me recently, like, I think I don't understand what's going on also inside a model, and I don't understand all the 2 million lines of code in a model. So for me, it's almost similar to a black box, the same way that we talk about it in AI. So I was thinking, how do you think that AI and emulated models, how do you think like they should relate to each other? How do you think like if like we should have like more AI models, or if that's like too black boxy or like too not transparent of like all the processes that's going on behind the scene? So yeah, I'll stop rambling. But
I think that's a really interesting question. And I think the comparison between AI and you know, complex numerical models is an apt one. You know, people worry a lot, the big hot button term in AI is, you know, explainability of models. But in practice, you know, if you have a little numerical blip that blows up into some, you know, big thing, and you don't understand why that is, or you don't understand why your model's creating, you know, 20 hurricanes at once or whatever, what does explainability really mean at that point? So yeah, I think at that point, having a more kind of end-to-end validation approach is kind of what you ultimately need. And I don't know if explainability per se is necessarily the most useful way of coming at it.
I mean, it is an interesting question. I think that it is important to make this distinction between physics-based models, physics-based, chemistry-based models that are at the fundamentally, they are based on the idea that we do understand something from the science perspective, and we've encoded that in some way. Does that mean that these models won't behave in ways that we can't understand? No, they will all the time, right? And in ways that are spurious all the time, right? But it's fundamentally different in my mind from what happens in AI, which is also very powerful, right? There's no question about that, which is about the idea of learning from data, right? And some fields are really data rich, and that's a great option. And NWP, especially climate, is not a data rich field, actually, relatively speaking, right? So we really do rely on the underlying physics. So I do think that they are not black boxes in the sense that, yes, they are hard to understand, but there is actually something underneath them, which is not just about learning from data, but is about making assertions about the physics is underneath there.
Yeah, it's an interesting question. I'm more on, I mean, AI can provide us also with insight, right? With patterns and others. And there's a lot of choices we make as part of physics parameterizations. And so we really don't fully represent the physics in our climate models. Or so I think for me, the rigor of really evaluating the models, treating them maybe as black boxes. How do they react to disturbances? How do they react to kind of I mean, we do all these ensembles, right? And it's a good question. How different is an AI model in this space? So I'm more, I think we need to be really have the rigor in evaluating the models, both on the physical side and on the AI side.
I think I just add one thing about AI and models. I feel like it's lost a lot when people talk about it, that a lot of the good numerical weather prediction with AI is actually from a reanalysis, not just a model. And so I think we have to be careful, especially at NCAR, that if we just replace our models with AI, job done. I think there's some super interesting things because suddenly ensembles are free, which personally, because I work with ensemble data assimilation, is really interesting. But yeah, I think it's not the model, right? It's the analysis, like it's the model plus the observations and the data assimilation that they're capturing with AI at places like ECMWF.
So I want to actually bring up a different theme because I'd really like to hear maybe from the audience about this, other panelists as well. And this is about this word that we use a lot, this kind of general term of open source, community models, open development. Like there's a lot of these words that we throw around, and oftentimes they mean different things to different people. And I want to maybe just open up a little time to have that conversation and hear from you, because I'm assuming most of you in the room, maybe not, but work on some form of an open or community model, because those are scientific codes tend to be. A couple of paradigms I want to just point out. I know that people in some parts of the community, Pangeo is one example, who think deeply about the nuances of what we mean when we say community model. So whether or not what we're talking about is that things are just open, meaning you have a sort of a core development group and they're the core developers, but everything they do is pushed out into the community, versus the idea that there's actually development happening in the community. A reason that this is really important to me is sort of a couple reasons. One is I don't know, do you guys know what the EMC is, the Environmental Modeling Center? So at NOAA, they actually do the model development for the National Weather Service. And I was sitting on their panel recently, a review panel for their modeling, and they have moved towards what they call a community model paradigm. And one of the things that they're experiencing as a result of that is they moved to that paradigm because they believed that would be a cost-saving measure for them, meaning they thought that they could get more development and better development done in a broad community as opposed to keeping a lot of that development in-house. And one of the experiences that they're having, and this will come as no surprise to anyone here, I bet, is that the amount of resources it takes internally, even to support a community development process, is enormous. And it's not always clear, I think, that you actually get more out of your software process if you open it up to community development, as opposed to keeping it sort of within a core team. I think the jury's out on that. I'd love to hear perspectives actually from this group about that spectrum of assumption, because I think the pendulum is kind of swinging back and forth about that. So that's an example. We have this example at Seaworthy, where we have basically the idea of code that is transparent and open, but a core development team. So development happens within a core team. Anyone is free to look at what we've done. And if they want to develop a special relationship with us and be part of the development team, great, but it's not just generally open. And then to contrast that with what you see with something like CESM, where there's like a true concept that you are sort of distributing the development load. So I just want to sort of open up that conversation, because I'd love to hear the perspectives and the experiential perspectives from this group on that tension.
Yeah, and I'm curious too, because I think the complexity of our models, does that really entice people to model? Because it takes a long time to understand CSM until you can contribute. So I'm curious about adding to that. Is that model really encouraging community in a broad way to contribute?
I maybe shouldn't say this, but I'm going to. It seems to me that NOAA's concept of community model is much like their concept of unified model. They said they were going to have a unified model, but they have 8 different models that call themselves the unified model. it's an institutional problem, really.
So I guess, Jim, maybe to generalize that a little bit, do you feel that that's just an unrealistic thing to try to strive for, or?
I think one distinction that I would draw when it comes to sort of NOAA's approach to community modeling, which they've, certainly gotten a lot more serious with, including with the EPIC collaboration now, is I think there's some distinction between bringing in outside developers in the hopes of kind of improving overall code quality, health, et cetera, versus scientific advancement. So as far as the question of, is it better to hire, a couple of senior software engineers, or is it better to build out the whole infrastructure for community engagement purely from a kind of operational support, keep the code stable? Then I would say, yeah, probably the community engagement is not going to be cost effective. But taking a more long-term view of it and the kind of scientific advancement, trying to invite community developers to bring in AI, which is still a relatively nascent effort within the Weather Service. That I think is where the real value of the community engagement side of it is.
All right, Ryan, why don't you, we do have stuff on, things are popping in fast now online, which is unfortunate because we're running out of time, but I assume yours is on topic, so why don't we go with yours and then we'll try to address some of the online.
I was just gonna, less of a question and more of just my experience, but it addresses things that have been talked about for the last few minutes, is that, overseeing a community model where 90+% of the PRs come from a small internal group, but we are putting it out there for everyone to use. And there's this kind of gulf in support where quick questions, we use GitHub issues, or we have a email listserv, we can respond to user needs that way. Very complex cases, we engage with stakeholders via, in-car contracting, right? We have projects that are paid for. There's this gulf in between of users who need more help than help desk, but don't have the resources or the problem scale to engage through the, in-car contracts infrastructure. And I guess I'm kind of struggling with, how do we support in a community model that group that's sort of between those two scales and poorly represented, because we don't have the budget to have someone whose full-time job is to support those folks, right? Because that was the cost savings of being a community model, right? Like I think like I said, it's not a question, more of just telling you where we're at and how does this where do you see this going? How do you think the best way to address that is?
I think maybe I'll just mention, because I think this is a related comment from Ward online. It mentions how, at Unidata, they obviously have a community driven development model. And he mentions how, yes, there's an overhead, but the benefits have far outweighed the costs. So, I guess that's the perspective that they have there. But yeah, to Ryan's sort of question, does anybody in the panel have any thoughts or follow-ups, or anybody in the audience is also welcome to join in?
I guess I could jump in. I think one thing I've been trying to think about is the sort of train the trainers approach. So I don't know if you've seen like software carpentry's approach, where they train people to be software carpentry instructors. I feel like with the community model, like we're never going to have enough support staff. You're always growing faster. So I think if you can, and it's this, I think it's the same idea as like the in-car hub concept. If you can just train a few people in like some key spots, like, I don't know, maybe it's the University of Michigan, maybe it's like, I don't know, some other community, and you can put someone in there who's like the more than basic support, not crazy support, but then it almost becomes like, I don't want to say like infectious, but they can become a source for their own community. So you're like I don't know, you're a connected node to the main development, if you buy that as an idea.
And I think adding to that, I think you bring up a good point, right? The scaling of support. I mean, the more, if we support every community member that needs support, we really don't have resources to do software development. So I think there's the train the trainer, maybe the community approach to really say, okay, certain topics we can't address. I mean, we just have to sometimes say no, which is the hard thing, right? Everybody wants to help. So this is really the hard thing. How do we say no and maybe getting the community experts engaged in answering those questions? So that's, and potentially maybe as part of the CSM process to train a few community members really taking on that role. But then how are they getting compensated? What's their primary role, right? I mean, there's a lot of challenges in scaling this kind of support model there. So I don't have a good answer.
I want to just a quick follow-up on that. Just a few reflections. So one thing I do think scientific software engineering and has an optics problem, and I'm saying this from kind of on the outside, which is that people don't know what you guys do. And they don't know how hard it is, and they don't know how long it takes and how much HPC it takes and how much expertise it takes. And when I say people, what I mean is funders, right? And so there is, I think, kind of a general need, and I know many people are aware of this, is to do somehow a better job of communicating the importance of the scientific enterprise, the software engineering enterprise for making science and commerce move, right? It is an engine for science. It is an engine for commerce. It is an instrument. It is a facility. It is infrastructure. Like nothing happens without it in a lot of these spaces. And that information really, I think, if you're just talking within NCAR, like I think NCAR kind of gets it. But it really has to do with the way that communication happens more broadly at some things like the congressional level, where they set things like NOAA budgets, NSF budgets. And I think one thing that this community can probably do a little bit better, right, has to do with really just the sort of the linguistics that you use when you talk, the semantics of the talking. So for example, the use of the word model. That means something different to almost everyone you talk to outside of this small community of people. The use of the word software, what does that really mean for a lot of people? So, I would emphasize in a lot of cases is that part of the communication challenge is about really speaking more clearly to an audience who is not a technical audience about what it is that software engineering is, which is really hard because it's a very abstract concept, but it's really important that we find a way to communicate that in a better way.
So I do want to make sure we get to one more online question before we run out of time, but I'll, if you want to give a quick.
Hello, this is Ed Hartnett. Glad you guys are all here. I would like to comment. There's a wisdom from agile programming, which is sometimes ignored in this conversation, which is that you need to focus on reducing your production costs on a continual basis. So doing software the same way that you were doing it last year is a mistake. You need to be saying, what are we spending our money on in software development, and continuously be looking at increasing your automation and decreasing your costs so that you can deal with your community. This is something that the NetCDF project does really, really well. And that's why with a very tiny staff, they're able to support the whole community very, very well, because everything that can be automated is automated at Unidata. Thank you.
Thanks, Ed. So I guess we've committed the cardinal sin here of not leaving enough time for the panel. I feel like that happens at every conference I go to. So I'm just going to steal a couple minutes from the break, if that's all right with people. And I just want to kind of finish with Caitlin's question online, which is, I guess I'll just read it if that's okay. There's a lot of interest in applying modern software processes and practices from the private sector to scientific software development. I'm curious which practices you found most helpful and which, if any, you found work less well or more challenging in a scientific context. And maybe I'll just sort of generalize that a little bit and say, like, for everybody who's here who wants to do something actionable that's sort of maybe a productive change they can think about in their scientific software design practices, support, teamwork and all that. What's one thing that you've found to be very effectual just in the context of stuff we've talked about today? And I'll ask each panelist to reply to that. And maybe I'll put you on the spot first, Helen, if that's okay with you.
Sure. I think just trying to make it a little easy for people to write bug reports, feature requests, just get people to chat about what they want to do. before, I mean, I'm gonna complain a little bit about scientists, before they come in with 10,000 lines of changes, right? And so I think just trying to focus on stuff we can do on like the month time frame, planning, thinking before we write a bunch of code. I don't know if that's very modern, but it's more modern than what we were doing.
I mean, in some sense, if we're not doing it right now, at least effectively, it's modern. Anybody on the panel who wants
Yeah, I
to jump
think
in?
for me, it's really, I think what the previous comment, automation and especially automated testing and in all dimensions, performance, functionality, all this. I mean, this was what we did at the DOE Exascale project. I mean, they set really aside, I mean, because sometimes the integration between HPC, for instance, and kind of GitHub is challenging, and making this seamless and really automate and test every change and have dashboards to look at performance and the functionality. I think that's one of the things that really helped us to be successful in the DOE project. I think we have seen some failure in some of the ASD projects where testing wasn't done as rigorous as it should have been, and then the question was about trusting the results, and so not doing that, I think, can really impact trust.
Yeah, I'll just second that and say automate everything that you can automate, and anything you can't automate, document it, including, you know, maintenance of your automation and so on. And then from there, you have to really stick to the premise. So the other thing is, once you've got the unit tests in place in your CI workflow, you have to require them. You can't let yourself backslide. You can't let developers say, oh, well, we really need this bug fix, so, you know, let's introduce like 3 more regressions because, you know, we just really want to get this in there. We'll deal with it down the road. You have to stick to your guns once you implement these systems, even when it's hard.
A point that I want to emphasize, and I guess I'm making sure I'm understanding the question, which is, you know, what can we learn as scientific software engineers from what happens in kind of more in the private sector software industry? Okay. So one big theme, this is a big thing that has to do with the focus on things that are useful as opposed to clever. So there is a tendency that I observed, which is that there's a lot of very useful things that are not publishable, that no one will think you're really smart for doing, but are of extreme utility. And I think this gets back to this question of, you know, can we work in kind of smaller increments around, like Helen pointed out, like a month as opposed to things that take 6 months. So one of the things that we work with over and over again, sort of coaching within our software team, is do simple things a lot, like a lot of very simple, useful things will add up to a really useful piece of software. Doesn't have to be clever, doesn't have to be novel necessarily. It may not be something that you're super proud to stand up at supercomputing and talk about, or even this conference, but a lot of times there's just that focus on useful and simple can go a really long way once you're doing it rapidly enough.
All right, well, I do want to.
Brian, really quick, the panel goes for another 5 minutes. The break starts at 10:10.
Oh,
So
okay.
we have, I did that on purpose. I gave a whole hour so we can answer maybe another question if we have time.
Excellent. Now I feel like I've cut us short here. All right. Well, thank you, Tasia, for the reminder. Okay. Well, that means we can jump into at least a couple of these comments online. So there's another comment from Sam, I think, to our earlier discussion. That's a perspective from, you know, the CTSM project. It's certainly, you know, helpful to have, helpful to be a community model and get that community development engagement. So I think that's another sort of comment similar to the Unidata experience. Okay, so it looks like the next question or comment was from Stuart. It says, is it unkind or professionally inappropriate to also remind external users of the basic statement, junk input data will generate junk results? Okay, so I think this probably ties a bit into the AI discussion and the ensembles. And let this responsibility of scientifically correct use be pushed to the users. Yeah, does anybody on the panel have a initial thought on that?
I don't think it's unkind. Oh, go ahead.
No, I was just gonna say, like, I don't know whether it's gonna get you helpful collaborators. I think you have to think about how you phrase that.
Yeah, I was doing the same thing. I think the principle is right. I would phrase it in a different way so that bring in people. But I agree. I mean, I think can't expect, right, to get correct science if you don't really understand what somebody is doing. And I think that's maybe the training aspect, I think, is key too. I mean, how do people learn how to use our models? They come to us, I think, most of the time, right? So I think really providing good training and talking about the challenges there, I think is key for that.
Well, I think this is actually a lesson that can probably be learned from the private sector. So, you know, there are lots of obviously non-scientific codes that are, you know, create whole companies around. And one of the things that they do is they have huge teams of user success engineers, which is basically like these people whose sole job is to work with users and make sure that they're getting their needs met by the software and they're using the software correctly, right? So that is, I would say, a massive kind of missing link that I see a lot in scientific software engineering. What that, of course, that takes a ton of money to actually support a staff like that. So I'm under no illusion that that can just happen. But I think it's just worth remembering that there's a missing layer that exists a lot of times within scientific software engineering that could help prevent some of those concerns around misuse of the software itself.
And I think just, you know, this isn't a problem that's specific to scientific open source software, you know, as we've seen in the past few weeks where there was, you know, the XZ library that does not really get the funding that it needs to have proper maintenance, and a huge exploit got put into it. So maybe that's heartwarming that like it's not just our problem, but. Okay, I think
sorry, one
Go ahead, Tom.
comment. I think the key is, I think it comes back to funding and convincing our funders that this is key infrastructure. And at the same time, right, the National Science Foundation is not very good in funding. I mean, it's our main funder. It's not very good in funding infrastructure. I mean, it's not just software in general. I think this is, again, we are trying to make the case. We're talking at the leadership level at NCAR to NSF to the different agencies, but it's challenges. And then it's even the funding level, right? There's, for instance, one good example is NEA, the National AI Research Resource. It's authorized for like $2 billion investment. And Congress hasn't done their job, right? It's authorized, but there's no money. And so, and I don't expect there be any money soon, but I think that's the case in a lot of these infrastructure projects where I think, again, it's communication. That's the best we can do. And finding partners in other agencies to do the messages consistent. At the same time, I think we need to say this is a competitiveness issue maybe as part of our economic competitiveness. But it's a difficult problem. There's lots of different priorities. So not very optimistic it's going to be solved.
Okay, yeah, since we're in extra innings here that I didn't realize we had, I'm gonna also mention Gregory's question and then we can wrap it up. So do the panelists see advocacy groups like Better Scientific Software, the US Research Software Engineering effort, Software Sustainability Institute, and et cetera, as being impactful in helping to inform funders in particular around model development challenges for software engineers?
Okay, so I'd answer that I love the concept. I had never heard of any of those three organizations. And again, the funders that we talk to are very often, you know, we're thinking about legislative advocacy at our organization in terms of bringing funding into the space through the channels of science agencies in the US, but we also work with philanthropic funders, right? And I would actually love to hear more about those organizations and what they're doing. Maybe they are effective on some level that I'm unaware of, but I would have liked to have heard of them. So.
Well, maybe part of this is some of them are fairly new, right? I mean, the software engineers, I think they just hired Sandra as the executive leader there. But I think it shows that should be their focus, to really advocate, and at the same time they are small. So how can this amplify it, and maybe the industry startup outreach? I don't know. I think that's a good point. I think, how do we amplify their voice to our funders?
Yeah, maybe I'll jump in on that one briefly as well, and say, just from like the software engineering assembly perspective that puts on this conference, you know, for us at NCAR, it's like, well, we are small enough and I would say focused enough on just sort of building inertia within our small community, that the idea of trying to then broaden awareness of it to, you know, external stakeholders, just, you know, it doesn't happen. So I think some of these other organizations are starting to get big enough that, you know, they'll be able to do that. I think USRSE in particular has a lot of potential there. But yeah, I'm glad you brought that up, Alicia, because it's, to me, it's like, oh yeah, I know of these, that's obvious, but clearly it's not outside of, you know, our small community.
We, at NCAR at least, we need to also start internally. I advocate a lot for investments in this space, and I haven't been very successful so far. I think we need to look at our budget, right? How does NCAR, this is for me, a budget shows where priorities are, and I haven't seen a lot of changes. We're hopefully in this ABR, we have another conversation around software engineering, the community software facility. And at the same time, it means for science organizations to say, okay, less science, more investment in software engineering. And that's a very, very hard decision for us. So
Yeah, I think USRC has been really good for the university community, and like the focus on professionalizing software engineering at various universities, some people doing work. I think BSSW is like quite national lab exascale focused. So I think Alicia's right. We're missing I don't know, the private sector connection there. And I know USRC has done a bunch of like funders series where they have different funders come and talk to USRC. But it's obviously not quite where we want it to be.
Yes, Alex, do you want to jump in as well and give a final thought?
I actually can't really speak to this point, so I also had not heard of these organizations, but yeah, I mean, I guess I would just kind of broaden the earlier point about sort of communicating these things, starting just within our organizations, understanding what's out there, and then establishing the need to get this information out to the broader community.
All right, thanks. Yeah, I think there's a sustainability problem with some of these as well. Like BSSSW is wrapping up or has wrapped up in a lot of its efforts. So, you know, having them be sustainable obviously is going to be crucial to increasing awareness as well. All right, well, I have now officially taken away some of our breaks, so promises made, promises kept. But I'd like to give a round of applause and thank all of our panelists. And thanks, Helen, for joining us remotely. And thanks to everybody in the audience who contributed as well. So we will take, I guess, now a 15-minute break, and there's some refreshments outside, and we'll start with the talks when we come back at, get this right this time, 10:30. Thanks all.
Thanks, everyone.
So I mentioned it outside, but just a heads up for everybody, we're going to get started again in less than a minute. So. All right, so the next hour and a half is going to be, we're going to get into the talks part of the conference. We have 3 talks that we will have until the lunch break. So each of those will be a half-hour block. And then, after lunch in the afternoon, we'll have another sequence of talks. So the very first talk that we have for the morning session, we have a remote presenter, Maria Patrou, and she's going to present Reaching version 1.0.0 on spectroscopy visualization tool SHIVER, I believe. I assume is the pronunciation. So Maria, please take it away, and we'll do a Q&A after the talk is over.
Awesome. Thank you very much. Thank you very much for having me. Today I'm going to present about SHIVER. I have been a research software engineer in Oak Ridge National Laboratory, and this is the project that we created an application about neutron scattering spectroscopy. In this project, Anders Savitsi was the computational instrument scientist. Ross Westfield, Chen Zhang, Peter Peterson, Dar Stinger, and myself, we were part of the development team. While we need to thank Alana Quexwell, who is a user experience specialist. So just to outline what we're going to see today, we're going to look into very briefly about neutron scattering and spectroscopy and how is what is the SHIVER application, what it does, and then we're going to look into very specific enhancements that we added in the application. The first part is regarding enhancements in the code base, user experience, usability tests, participating in the OpenSSF best practices batch program, and the conda package regarding deployment. And the second part is more about the software development process and some good practices that worked, especially for me, when contributing in the code. So what is the science? It's material science in neutron scattering. That is an experimental method that uses neutrons as they pass through materials, which we call sample, to reveal the sample's inner structure. So overall, neutron scattering is measuring the probability distribution of finding neutrons in a coordinate system related to the sample physics. So to look like a little bit how it works, we see in this figure how there is a beam of neutrons which is spotted with the gray spots that we have in the Spangration neutron source facility here in Oak Ridge National Laboratory. And these are the beam monitors that they show how the neutrons are moving towards the sample, which you cannot quite see, but it's behind these panels where these axes are met. And when they hit the sample, then they scattered, and then there are these panels, which we call them detectors, imagine them almost like cameras, that then they collect information about the neutrons that are scattered. And in this case, you can see that there's different colors. A yellow will mean that there's a higher probability of neutrons hitting that spot. So there are various techniques for neutron scattering to study the material. Here we look into spectroscopy. Spectroscopy focuses on interaction between atoms and the material itself, looking at a model of a solid sample with atoms as blue balls, and there's bonds as springs. In spectroscopy, we care about the bonds, the strength of the bonds by looking into the different vibration modes. So how will look this kind of data in spectroscopy? Imagine that the data of interest are usually visualized as four-dimensional histograms, plots of neutrons as a function of physical quantities related to the sample. And here you can see some examples. Here we have 1, 2, and 3D-dimensional histogram slices with color maps from purple to yellow that reveal the probabilities of neutrons. So SHIVER stands for Spectroscopy Histogram Visualizing for Event Reduction. And it was built, the idea behind SHIVER is to build a software in order to visualize spectroscopy data in a user-friendly manner. And the project started from a prototype, from a script, to ensure correctness of the data, processing, and then we started building the application. Now the application has the backend where are the algorithms for data processing and the frontend that is the graphical user interface. Overall, it's statistically more accurate and faster than previous solution. However, in this talk, we will focus more on the software development and deployment of SHIVER, and we will not go through the science that can be performed using it. So in this terms, what SHIVER is a desktop application written in Python in the field of neutron scattering for spectroscopy. Users can load multiple unprocessed data that each one of these data contains information about a specific experimental condition. So this file will contain parameters about the instrument used, about the sample itself, and about its neutron separately. Then users can transform this multiple data together to some quantities that are related to the physics of the sample. Then they can store it in an intermediate data structure, and at the end, users can generate a normalized histogram and visualize it. It is based on the Mantit software suite, and it uses a lot of the concepts, a lot of the APIs, that is the workspace, that is a data storage, data structure, and algorithms that they are used for data processing, data reduction. Today, SHIVER is open source, and you can find it as an Anaconda package, or you can save and download it through this as a GitHub repository in this link. And this is how it looks like today. This is the first screen. So the moment you start SHIVER, you see the main screen. It has two tabs, the main and the generate. And here users, they can load previously processed data. And then they can add the parameters that they want in order to generate various histograms. Now the focus here is the visualization. This was the most common action for the scientists. So even though it's not the first, this is the one that the program starts with. In case users, they want to generate, to process data, they can go to the second tab where they collect the raw data that they want, save them, put the names, other parameters to reduce the data, they generate them, and they can either go back to the main tab and visualize them, or they can save it and use it in the future to either visualize them or process them further. This is how we can look into these plots. These plots are generated from here, and as you see in this example, there are 4 data sets that they are loaded, and one is selected, and based on the type of histogram, either 1D, 2D, 3D, we can create these histograms. So the first thing I would like to include as an improvement is the usability tests through a user experience workshop that we did with SHIVER. So user experience includes interaction with the user with the application, not just the user interface. And there are various principles and patterns that they exist. For example, in a web application, we have the layout of the UI, the design of the UI to set in a way based on the on specific eye tracking patterns like the F and the Z patterns, make them more better depending on the type of the text, the context that we want to show to the users. And then we have the Jacob-Nielsen's usability heuristics that include consistency, for example, be consistent in your application, have certain standards, provide help to the users, provide documentation, and etc. So in this workshop, we put under for testing the most common functionality, and that is to make plots. And after we talked about the SHIVER usability, in the end, we created a scenario where we had multiple users creating a plot. So we gave them instructions and we told them to follow certain steps. So in the main tab, upload data, set the parameters for 1D or 2D plot, and then make a plot. And I'm gonna leave this for a minute just to show you what was the original flow. And as you see here, the user has to click the button and then load a specific data file, think of it. And then they will have to right click, set as data, and then they will have to set for a 1D case. So if you have 1D cut, you need to put a step for the histogram. When you click histogram, then this intermediate data is created. You right click plot 1D, and then you have your plot. But there were difficulties. So if you don't follow the plot, at least back then, you will get error messages. If you click histogram, then it tells you have to load for the data. Then eventually when you put a specific data file and you click again, then it says you select the data workspace. So now you need to find how to set it. And then at this point, it asks for histogram parameters. So you need to put a step, that's why there's this background box almost there. And then you need to right click in order to actually find, to actually see the plot. So yeah, let me go back to that. So, okay. We're back. We're really back. So what we realized is that there were issues, and then we wrote down the issues. The first is that they couldn't identify the workflow. The users didn't know where to start and how it works, and they couldn't make the plot. Then there was an issue with the button itself. They couldn't also understand what is this button for. They couldn't find the plot, the purpose of the parameters. Some of them, it wasn't quite clear. The buttons, the sections, what are they for? And then they have issues with understanding the right-click actions. Overall, they needed guidance. So we made some changes because of that. We added input value validation with button deactivation and activation. What I mean by that is that the button would not be activated until all the inputs are valid. And instead of having this background box, now we have a red borderline. Then we included informative error messages for the inputs. There was we renamed some labels and we added some tooltips that they provide information about its parameters. There was this explanation of the icons. And then we simplified the process of generating the plot. And on top of that, these changes were applied in other places of software. And if I go back to it, if you excuse me, for 1 second. I just want to show you how it looked like. So now we have these borders here instead of here that was only the background box. And now it indicates in a way where to start so people can load, for example, a data Nexus file. And here below, as you see, there are the icons and explaining what it's, the name of the icons are for. Then you see these tooltips. If you hover around here, it's very fast, but it is showing this yellow there. And then, yeah, in this case, I put some minimum and maximum where they still aren't until you actually put both of them and they are correct. Then the moment you click histogram, the histogram appears. So, excuse me about that. That's the last thing I'll do. So that was pretty much the changes that we added to simplify the process. Now, moving away from the UX, we included in the project the participation of OpenSSF Best Practices Badge Program. So OpenSSF Best Practices, which you can find it in this link, offers a way for projects, for FLOSS projects, pre-libre and open source software projects, to show that they follow best practices. And there are different criteria and badges, so they contain a series of criteria that the project can abide, and by fulfilling certain criteria for a project, the project can obtain a badge. An example will be that the project must provide basic documentation, for example. And so what we did, we created a profile for SHIVER, and we went through these criteria that they are grouped into various groups related to basics, change control, reporting, quality, security, and analysis. And then we went through it, and based on that, we added some documentation about testing, a reporting process, and in the end, we also have technical documentation. And today, SHIVER has the passing badge, and it looks like that, and you can add that to your GitHub repository. One last improvement relating the code base is about using Conda packages. And as I mentioned before, SHIVER can be downloaded as a Conda package, and it is in the Neutrons directory. You can find it here. So the way that we have it configured is part of automated actions, and we use the GitHub actions to build automatically at every request to make sure things are still working. And then we upload to Anaconda from a specific branch after we mark the software as ready for deployment with a new release, with a new tag, and then we include release notes in the repository. We also, during this process, we added documentation for configuration for the projects that we have in the project, in the Neutrons project, to use it in the future. The advantage that we have now with this is that we can trace the software version and dependencies as the software grows. And then we can also distinguish between the development code and the production code. Last thing that I would like to include is about software development cycle process. So leaving behind enhancements specific to code, we took and we focus and more specifically on the development side and what is needed for the software to be marked deployment ready. In our team, the work is organized in an agile software process or in different sprints, iterations, and there are different assignments that can be in features, bug fixes, and other enhancements. The people that are involved are the users that are going to use the software, the computational and instrument scientists, and the development team. So the responsibilities for a person are different. We have the development team let's say, research software engineers that they they design and develop the application, and they create pull requests, they review pull requests of their colleagues to make sure that the code has a certain quality. And then we have the computational instrument scientist, or CIS, who is the product owner, who has the domain knowledge on the material science, on neutron scattering. And this person defines the functionality and tests the developer's implementation. The users are the ones that they have the more specialized domain knowledge, and they use the application to do the material science. So here we see, I want to show how this actually works, how it interacts, how these people interact with each other. So imagine that the user might need something that it does not exist, or they cannot do it in the software. Then they describe their goal to the CIS. And the CIS, the computational instrument scientists, they create a prototype, they create a script, and then they send the requirements to the research software engineers. So they parse the knowledge, domain knowledge in a relevant way to the developer. And then the developer now is responsible for writing the code that implements these requirements. Then the developer can demonstrate, can do a demo, and show the software to the CIS, who will test it. At this point, maybe there might be a feedback and a little bit of back and forth between the CIS and the RSC to ensure that things are working a certain way and the application fulfills the goals, and also for the sake of the application. Now, when it is tested and it's in a satisfactory level, then it's sent back to the user, who now can execute the data processing using the software. But certain things to consider here is that we're talking about software that is very specialized, that is novel, and we have people with different backgrounds. That means that there might be a misunderstanding. A good practice that has worked for me is to have a bidirectional communication throughout the assignment. So not just in the beginning and at the end, talking during the assignment, and then having incremental demos with the CIS. Also having flexibility within limits. As long as the physics is correct, adjustments in the requirements can be made for the sake of the application. And especially for my perspective, I wanted to mention that I am a new member in the development team, and it helped me a lot to have a constant communication with the CIS. And the reason is that I was reassured that the code implements what the science needs, and I was also participating in formulating this solution. From the CIS perspective, from what I know, they were watching their vision taking place. They would understand how the vision becomes a final product. They will see, it was helpful to understand the code implementation, because then they can find spot to break it. And that makes it a more robust testing. And remember that CIS and developers will look into things in a different lens. So to conclude, we looked into different levels of software for improving its quality and the importance of human factor in all levels of application lifecycle. Today, SHIVER is used by scientists. Overall, we have some good feedback by the users. We do add some enhancements, some minor bug fixes, some updates, and we are looking into components worked efficiently to apply them in other projects. Thank you very much.
All right, thanks, Maria. So just a reminder for those who are in the audience, feel free to come up to a mic if you have a question, or just raise your hand and we can give you the plushy mic. And if you are remote, just put your question in the Slido and we can take them as time allows. It looks like we have about 5 minutes for questions. I guess I'll start a question while we wait for people to collect their thoughts. So I have a lot of questions that I could ask about the UX workshop, but I guess maybe just broadly, do you feel, based on that experience, that that was the right time in the project to ask those questions? And I guess more broadly, do you have any lessons learned from that UX workshop?
Yes, I think, I mean, it would be nice. They say it would be sooner the better, but I think looking into the process of the main, that the SHIVER is about creating normalized histogram and visualizing them. So looking into how users actually will use it, it was an important lesson. And we did make these adjustments that I mentioned, like simplifying the process, looking into the interactions in a way, ensuring that they will not do the wrong path, they will make the correct path. And what I mean by that is that by deactivating the button, we pretty much ensure some kind of guidance. And the lessons now that we learned, like this kind of behavior, we will be applying it in other projects too. So yeah, definitely, at any point, I would say, and even in the future, at any point of the development, it will be nice to look at it and see how this software is useful, how is it used by the users, and make sure that it's as easy enough, as user-friendly enough as possible.
Thanks. Yeah, that makes sense. Anybody in the audience have any questions for Maria?
So I have a quick question, mostly from inexperience. How difficult was it to implement this into Conda to provide an easy way for the users to download it and use it themselves, since I've never implemented anything in Conda?
There are instructions that you follow about creating a YAML file. There were some, I mean, you have to follow the instructions, a little bit trial and error, but it's doable. There is a lot of information out there. Yeah, I would say it's just a matter of, however, reading about it and working your way with that. And I will also recommend it because it did help us to trace what the dependencies are for the project.
Thanks.
All right. Any final questions for Maria? If not, thanks again, Maria. Give another round of applause.
Thank you.
And then we'll move on to the next talk, I think, in person this time. So yeah, I'll just take a second to get everything set up here. And in the meantime, I'll introduce John Cazes and Amit Ruhela and present 3 years contributing to improving big data applications support in HPC.
Morning. So I'm John Cazes from the Texas Advanced Computing Center, here with Amit, also from the Texas Advanced Computing Center. This is a project we began in 2020. All right. Which way advances?
Oh, just do that. And then there's also a pointer that you can point at the monitor if you like.
Whatever. Okay, so first, I'm going to start with the name of the project, BigHPC. So in 2020, we were talking about big data and HPC and how they had different sort of workflow characteristics. And how could we create a framework that could support both of them and run it from a data center and sort of make it independent of the underlying architecture? And so we had a project that we called BigHPC. Of course, today we would not call it that. We would probably call it MLHPC, because every time you hear big data, think machine learning, because that's what it is. And so one of our problems was mostly heterogeneous hardware. In 2020, most of our work was still for scientific computing, HPC, from what we saw from our users, mostly CPU bound. The ML work, of course, was all GPUs. We had a small fraction of HPC on GPUs, mostly with community codes, and they had different types of workflows. They had different I/O patterns, different communications patterns. And the idea for this project was a way to create a framework that would support both and give the people that run the data center a way to manage it efficiently. And so this started in 2020 with our partners in Portugal at the Miho Advanced Computing Center. And we both have several architectures. TAC has Intel, TAC has AMD, TAC has NVIDIA GPUs, and now we're about to stand up a system with NVIDIA ARMs. Miho has a new system with AMD CPUs, NVIDIA GPUs, and Fujitsu A64 ARM chips. And so the idea was to create something we could run at both places. Now, I will preface all of this with, this is just a prototype. What this project produced was a prototype. It is not in production yet. If we get further funding, we'll go further and maybe actually open it up to real users. Okay, and so the idea was, how can we support these workloads? How can we support them in a way that we can provide an environment for either set of users to manage their workload, and we can control it remotely? And the conclusion we came to was we're going to use containers, because also the idea was to try to make this as agnostic as possible to the underlying hardware and the center policies and whatever is deployed. And so the container decision was key. And so the main things you'd have to do to integrate this into any center is build a template container to allow users to build on top of, integrate our framework with the scheduler, with whatever scheduler you're using. And so that was our goal, to create something that could be pretty much deployed anywhere. And so we had three main things we wanted to do. I'm not sure this is the way I would have ordered them. I would have probably put deployment as first. How can we deploy these containers in a way that the user can just request a job, get what they need, or build upon a template container and have it run? And then I would say, after that, monitoring to make sure it works. And sort of the final thing, although this is the one I'm most interested in, is storage performance, right? So these workflows are quite different. HPC is mostly write, a burst of read at the beginning, and then burst of write. ML is mostly read. And trying to manage this across the file system can be difficult. Parallel file systems are not really built to interact with schedulers or jobs, or have the concept of jobs. They understand I/O tasks and they understand nodes. And this was an opportunity to change that, to insert a middleware. And since we're using containers, basically, we can insert these features into the containers. And so the user is mostly unaware of what's going on underneath the covers, but we're going to control their I/O. We're going to monitor everything they do, and we're going to control the deployment of these containers. And so this is sort of a high-level look, and I'll go into a more detailed one, I think, on the next slide. And so there are three components we worked on: the virtualization manager, the storage manager, and monitoring the back end. And so each member of the group had a component. TAC's component was the virtualization manager, which I'm going to go into more detail when he gets up there. In Portugal, they worked on monitoring the back end, and they worked with us to sort of monitor the right things, get the right counter data, and the storage manager. And I worked a good bit with the people doing the storage manager, because that's what interests me. And storage is a huge problem on our system. In general, when a user gets disabled, it's because they've done something to the parallel file system. It's a shared resource and most people don't think of it that way and they overwhelm it. And so the storage manager gives us the opportunity to limit what users can do and basically prevent them from impacting everybody else. Oh, back to the containers. Like I said, we decided to go with containers because this was the easiest way we felt we could make a generic framework that could run anywhere. Just about every system now that we know of, right, supports containers. I know at TAC, our life sciences group had to move to containers to support their users because otherwise they were requesting software updates like every 2 or 3 weeks. They're like, oh, there's a new Python script out. Can you install this? And it finally just got to where we said, no, you install it with Singularity and you run it yourself. And we've even set up some tools, I can't remember what it's called, where basically you can set up your own modules. So when you load the module, it automatically downloads the container and runs it for you. And to you, it looks like it's already installed. And so here's a more detailed look at the architecture. For the end user, basically what we need from them is either a custom container or they choose their own template and they just use that. We store that in a repository. And then when they request a run, that gets loaded onto the actual compute node. And within this container, we have our controller. So we can measure what they're doing with I/O. We have our monitoring component, so we can see how they're operating. We get counter data. And later, there are some examples of the dashboards and what you can see from the monitoring. And the storage manager, the nice thing about this storage manager is now we have a global look of what the jobs are doing. And we can set QoS details for each individual job. And so this is the part I'm most interested in. So that's why I'm talking about this part. Let Amit handle the rest. So the idea here is if I know what your job's doing and I know what all the jobs are doing, I can maybe give you a max and a min QoS. When I say QoS, quality of service for read bandwidth, write bandwidth, and metadata operations for the whole job, not just per node. This allows me to more effectively manage that, right? So if you're the only one doing I/O, then I just give you the max, right? And you get whatever you can. If somebody else spins up a job and maybe I/O is really important, so they have a higher QoS, they have a higher priority, I will drop your job to the minimum and let their job run at a higher priority. And also, this helps me save the file system. So one user can't take down my file system and ruin it for everybody. And the idea here is through this, we can look at both how HPC works, which is write intensive, and how big data works, which is read intensive. And hopefully support both. And the user doesn't know anything. They just launch their job and it runs. Now, the only thing I will say that might impact the user with this scheme is their I/O times might be fairly variable. If the system's under load, then the I/O is going to take longer. So here's a very detailed description. And really, all I want you to take from this is at the low level, we have something called paddle. As far as I can find, it doesn't stand for anything. I'm not sure why they called it paddle. But that's the part on the node level that manages all the I/O. And it communicates with a global controller. And this is all within this container. If we were outside of the container, we couldn't do this. And when I first started working with these people, I got excited because, oh, we can fix Luster. Finally, we can do something with Luster. And they were like, I don't want to tie this to a specific file system. It's like, okay, I'll go with that for now. But so this runs at the node level and it gets its directions from something called SHIVER. And so this is the global controller. So this is the one looking at all the jobs that BigHPC is managing. And it has an idea of sort of the total read, write bandwidth of the system and how much metadata it can control. And so what happens, whoops, how'd I go backwards? There. So what happens at this level, right? It's constantly communicating with this global manager. And what it's done is it's wrapped all your POSIX commands. So open, read, write, it goes through this. So you don't have to do anything in your code, and it knows what you're doing for IO. And so it has a local QoS for the job. So it knows sort of how much as a whole the job can read and write. And it can communicate within the job. So at the paddle level, it knows what the job's doing. And that is communicating with the global controller, SHIVER. And so it can change the QoS on a job. So let's say one job finishes, right? Nobody else is doing IO. So it communicates to that job and says, oh, you can run max IO now. So go ahead and ramp it up. And this has been tested on this early implementation up to 2,500 clients. And just recently, they've made some improvements and they've gotten up to 10,000 clients. And they can update this like every 2 seconds. And they were talking to us the other day and they thought that wasn't quick enough. And we're like, we don't respond to file system problems except in 15, 20 minutes. So this is a lot quicker than we can respond because we have no mechanism to do this automatically. So from the data center side, we respond just by watching the file system and the load on the servers. We see something go up, we can go monitor jobs and see which job seems to be causing the problem, pause it, see if it goes away. If it goes away, okay, it was this job. If it doesn't, we have to go look. Because this is really more of an art than a science on the data center side from what the admins do. And this is why if you've ever been disabled at a center, and they couldn't tell you exactly why, and it was something to do with the file system, it's because they're not exactly sure. But hopefully this will prevent all of that. And so I'm very happy with how this has turned out, and I'm hoping that if we can implement this in production, it really improves our uptime and our user experience. Because the other idea here is we want to give the users a way to easily get on our systems, no matter what they are, whatever architecture. I give you a container, I say build on top of this, and then you'll be able to run on our systems. Okay, Amit.
Thanks, John. My name is Amit Ruhela, and I'm a manager in HPC Tools Group at Tech. So John has already given you a brief overview of this BigHPC project, and he has mentioned about the software-defined storage component, and now I'm going to talk about virtualization manager. Well, basically last year, I think I presented one talk where I showed I can run a container at the scale of 8,000 nodes and containing like 400,000 container instantiations. And that worked pretty well, and that showed very low overheads in running the containers at the scale of like full scale of Frontera systems. So that was the smallest study that was started. That's where we started with, and then we expanded that study and showed like we made it complete BigHPC project and showed how even like as the theme of this conference is like how you can improve softwares or how you can run better on systems. So this BigHPC project is very aligned to that and showed like you can build the containers, you can avoid the issue of like changing architectures and avoid the issue of all those new things or newer architectures coming up and run the containers effectively on variety of systems. So and now let me go into the virtualization manager, which is the core component of this project. And this manager is basically responsible for coordinating all the components of BigHPC. So it's a tool which allows end users or system administrators to submit the workloads, to upload the containers specific to the to a given applications. And if the users don't have optimized containers, they can download the templates and add their applications on top of that containers and then submit again to the to this infrastructure and execute workflows. Virtualization manager coordinates all the tasks, like whatever the workloads that has been submitted, it allows them, it coordinates with them, allows them to run optimally, And it also initializes the other components like monitoring components, storage components at the node and job level. Primarily, it consists of three components. Two are that shown here, scheduler and repository. But if we'll take a look at this complete architecture, so here I've shown the command line interface, which is used to submit the commands, basically the workloads to be run on the on this BigHPC framework. So users can submit the jobs from this command line interface, and administrators can use this interface to manage the workload execution, to manage the variety of queues that are being used within this workload execution. So on bottom of this screen, we see HPC clusters, which contains login nodes and compute nodes. And compute nodes each have multiple cores. And on top of this cores, one of the BigHPC component, which is called executor, is running. So do we have a highlighter? This one? Okay, so this HPC clusters containing the login nodes where exactly the reservations are being made. Reservations are basically what I mean, big HPC reservations, not the other reservations which people do it all the time on HPC. So whenever a reservation is made, let's say a reservation of compute node from 1 to n from k reservation is made, then on each reservation, on each node, we also create an instance of executor. And this executor is being downloaded from the controller to the executor when the reservation is made. And this executor is responsible for executing the workloads. Not only executing the workloads, it also creates the instances of software-defined storage component, which is basically a paddle. And then also the instance of monitoring component, which monitors or which collects all the performance matrices and send back to the to the external BigHPC framework. If we look at the virtualization manager, we have two components, controller and the repository. Repository contains all the containers of all the workloads that needs to be executed. It also provides an authentication mechanism for restricting containers to be accessed by only users who are actually the developers of that or who have the right permissions for that. Then we have other components like getting the templates or actual containers from the database. And then on the other side, we have a controller which basically receives the command from the users or the administrators. And then based on various scheduling algorithms, runs the workloads over to the HPC clusters. So here we just restrict ourselves to two scheduling policies, first in, first out, FIFO, and the fair share algorithms. But anyone can plug in their own policies, scheduling policies to schedule workload based on different priorities or different weights as per their requirement. So so the entire logic is like this. Whenever users submit workload requests to the controller, they are being queued into the controller's queue. And then there is a cron job which launches every second or whatever number, whatever the amount of time we have defined. It launches a job, it launches basically a program, and then which program looks for if there are any workloads to be executed. If there are a couple of workloads to be executed, then it finds out how many nodes does it need, and then create a big HPC reservation on the HPC clusters. So the controller is basically creating those reservations and also tearing down when the jobs have completed or failed, or whenever there is no need of having the reservations to continue further. Then it also creates it uploads an executor, which is basically a singularity image onto the compute nodes, which instantiate other components and runs the workload, and then at the end gets the output of those workload execution back to the controller and back to the command line interface where users can see how the workload have been executed. The next component of this big HPC framework is monitoring, and any monitoring contains following steps. The first is extraction of matrices on the compute nodes. and then they have to be translated into a format which can be understood by the analytic tools. All those transform matrices are then sent to a common central point where they are being aggregated and then stored into a database. In our case, it's a from scale database. And then they are being visualized with some dashboards, alarms, or analytics engines. The major goal of monitoring interface is HPC contains so many nodes, and the scale at which HPC works is too much. Too many matrices are there. Even if you look at the common systems, any system, there are thousands of matrices that can be collected, and it's pretty difficult to analyze those matrices. The other issue is we don't have any HPC system don't provide all set of privileges. It's all like, well, there are some basic privileges that have been provided, and you cannot collect all sort of matrices because of those limited privileges. Then collection, processing, and communication overheads you have to minimize. You cannot run your monitoring software which impacts the performance of the application. So the major goal is how you can build a monitoring framework which can give you comprehensive information, as well as it's a lightweight. It doesn't impact on the other system resources. So this is an overview of our monitoring framework. So in this framework, this is a Monica, which is monitoring in containers. This is an external interface, external component. And this one is the HPC cluster where the component Hector is basically a local component running on a node collecting the performance matrices. So this Hector component collects all the performance matrices and then pushes back to the VM agent, which is running on the which is running externally to the compute systems. So all the matrices are being pushed from Hector to the VM agent, and VM agent then collects and aggregates all those matrices and stores in a timescale series database. And those matrices can be visualized through a Grafana, which is a visualization tool, and they can also be queried by the other SQL tools like PromQL or SQL. So this is a high-level overview of Hector, which basically reads a YAML file, which basically reads a YAML file and find out like, does the job needs to be, so the fact is, we allows multiple jobs to run on a given node. And at this point of time, we restrict only the number of jobs, which are basically equals to the number of sockets on a given system. We don't want to go even further, fine level of granularity. We don't want to run jobs at just core level. We want to run jobs at the, like, even if a job runs, it should be for monitoring purpose, we want to collect the matrices from the socket level, not from the core level. So we do collect performance matrices at core level, but they are being combined together for the socket level. So if there is just one job running, then it's just a node level monitoring. But if multiple jobs are running, then we can monitor the jobs and based on the job ID. So all such matrices like disk, network, process, CPU, memory, luster, InfiniBand, and other systems load information are being collected, and they are translated and pushed back to the virtual manager VM agent running outside the compute system. So I just want to highlight a couple of slides which shows what information was collected. And this is just like the CPU information, where it shows like you can select all the combined in matrices, or you can go node level and see how the CPU utilization was there. Like what was the CPU usage, frequency, and then we can also see the context, which is interrupts, software interrupts, syscalls, etc. This is the memory usage. It shows how the memory was used on a given node. It shows the amount of swap memory and the memory utilization over the given amount of time. Then this is the kind of network usage, how much amount of memory was, amount of data was downloaded and uploaded on a given node. Then we have a GPU utilization, which shows GPU utilization, GPU temperatures, and other information like how much memory was consumed on the GPUs, how much memory was used free, and so many others. This is the earlier slides were node level, but now we can also visualize the information at process level, and it shows that as you can see, there are thousands of processes running on this, I think, TensorFlow, some kind of application, machine learning application. And yeah, it's a TensorFlow CNN benchmark. And it shows how each of the process was behaving at given point of time, what was the CPU usage, memory usage, and so many other information in terms of like process. Then we have a file system. The Lustre is the file system which is used on our Scratch file system, and this slide shows almost like I think 22 operations get attribute, open, close, read attribute, memory map, and so on. So all of these operations are being shown for each of the node, and then you can also see the Lustre operations per second and Lustre total read and write bytes per second, and so on. These are the Lustre this is the information in the operations view, like for each operation, how the performance was look like, what are the most time consuming operations, how they behave over the given amount of time. And this is not Lustre. I think these slides are a little bit old. I modified them in the morning, but somehow they have been not updated here. So this is the file system view. So we have three file system: home, Scratch, and work. And you can visualize this information with the file system wise as well. So as a whole, we develop several components at the local level, which is the compute node level, the storage controller, data plane, actor, and VM executor. And then at the global level, which is outside the HPC systems, like storage global controller, basically SHIVER, Monica, which is monitoring agent, and then VM control and repository. These are all the components developed at the different sites, and then they were all combined together. And we have also developed, apart from the command line interface, we developed the web interface which is more intuitive for non-HPC users to upload the container images, submit the workloads, or for the administrators to define different policies or define the port and socket ID information. So as a whole, these prototypes were developed. I just covered it, and the final summary is we basically the 5 institutions from Portugal and US, they develop a unified interface for running parallel and big data applications at HPC centers. These container-based solutions, they definitely provide the portability and ease of access and deployment. And then the storage quality service policies can be enforced to run the containers in a way so that like everyone gets the fair share of the file system resources, and nobody should be banned on our systems for misusing or abusing the systems. And then the monitoring and visualization tools were developed to understand the cluster utilization and make the policies more adaptable to run the containers. So right now we have done the studies over TAC and MAC systems at some test level, but we want to go into the production systems, especially the software-defined storage, which complements our like Lustre doesn't provide you a way of restricting applications to work on a specified quality of service level, but this software-defined storage component definitely help us to or complement us to run the applications with defined quality of services. So we would like to add that to our systems, and we would like to extend our repository to contain more applications or machine learning workflows, which have becoming more popular nowadays. We would also like to optimize the storage solutions to run at more final granularity, and then enhance our performance analysis tool to have more comprehensive information, or the information that can be understood. Like we don't want you to provide thousands of interfaces and let you to find out your own what information is useful to you. So we want to make information more appealing or find out like what was the issues while running the workloads on our systems. So now I would stop here, and I want to thank all these institutions running, developing this BigHPC framework in Stack, Mac, Tech, Texas, University of Texas, and the Wavecom for commercializing this project. Thank you.
All right, I think we are actually at time. If there's a quick question in the room, we can take it, but yeah, please.
Yeah, thank you guys for the presentation. Very interesting. I'm curious about the extent to which the use of containers for the users allows users to not have to worry about hardware. So in particular, I'm curious about, like, for an MPI application, does a user need to worry about having their containers MPI library be configured for a certain network fabric or anything like that? Or is that something that is that can be pretty transparent to the users?
There are basically two approaches for running the MPI programs. One, to embed the MPI within the container, or you can use the external MPI and bind mount that MPI over to the containers. So we use external MPI to launch the containers, but we also allow users to embed their own MPI within the containers. So external MPI just launching containers, internal MPI doing all the communication operations, and that worked pretty well. And I showed it at the scale of like 400,000 containers. There are certain issues. I won't say that containers are always portable or always work well, because you can't run a x86 container or IBM systems. You can't run, there were issues in running the containers over to the GPUs. And we saw like some libraries, like NVIDIA libraries, they allow you, they have a flag like --NV to push their libraries onto the containers, but that doesn't, like, it helps, but you cannot run all the time on all the architectures these containers. There are difficulties, especially the GCC library. Sometimes they cause issues because of the incompatible versions. Like if the external GCC and the internal GCC is different, they might cause issues. So, but most of the cases we were able to run the containers at a large scale. And I think, yeah, we were successful to some extent and leverage the functionalities or features of containers.
Very cool. Thank you.
Thank you.
All right, thanks again. All right, we have one more talk before the lunch break, and this will be presented by Jonathan Joyce. It's titled "A Cloud Optimized Workflow for Serving Model Data."
Okay, great, thanks. All right, so hello, everyone. My slides just here. There you go. Hi, everyone. I'm Jonathan Joyce, software engineer from RPS Group, a Tetra Tech company. This group is, Tetra Tech is an environmental consulting company. And within my very small group, we do a lot of consulting work for IUSE, have a cooperative agreement through which a lot of this work was done. So today presenting a cloud optimized workflow for serving model data. So a lot of this work was made possible through this Reaching for the Clouds project through IUSE, which is the Integrated Ocean Observing System. And this is a 3-year project. We're coming to the end of year 3 now. So mostly wrapping up and reporting. But the whole idea of it was to kind of reimagine how IUSE can do their data management in a cloud native environment. So we're looking at a lot of, what are the best tools and technologies out there right now so that we can kind of start fresh and, continue to advance this.
over a long period of time. So we're also, very focused on using best practices from software engineering, as well as taking ideas from analytics, AI and data science for how we can organize the data better to be able to, use those things. And then finally, a lot of this is focused on creating open source communities around these ideas. So I'd like to acknowledge the project team that's made this all possible. We have a pretty solid software engineering team at RPS. We're like mainly software engineers, not half part-time doing science. And so we have a lot of solid best practices in place. We containerize everything. We run unit tests, et cetera, et cetera. And we're also not just our team, but we work with a lot of external contributors as well. You could see there on the right, who are also using these tools for their own use cases. And of course, I'd like to thank the IUSE Program Office. This is really some visionary leadership that's made this research in computer science and software possible. So I know probably not as many people here. I know this is probably a very atmospheric focused community. I worked at Ceres Global Systems Lab for 7 years before joining RPS. So IUSE is the Integrated Ocean Observing System, falls under the National Ocean Service, which is under NOAA. And IUSE is itself comprised of these 11 geographically dispersed regional associations, and each regional association conducts the forecasting for their area of interest, and then they collect the observations, usually in the form of buoys, high frequency radar, and gliders, and they do all this data management themselves from the ingest, and then making sure that the metadata is compliant, and then serving that data. So there are actually here 11 different software systems and architectures serving this data, and in many different ways, different websites. Like for example, one of the challenges, especially on the East Coast, is like if you are looking at a forecast and you end up like on a boundary between two domains, then you need to go to another website, look at a different forecast to see what was happening, north or south of you. So with this, we saw just based on that the cloud really makes sense for this type of organization. They're geographically dispersed. Unifying that software architecture definitely makes sense. And so looking at cloud, we first kind of drafted a system architecture. So looking at the underlying components, should we use Kubernetes? Where can we use serverless, et cetera, et cetera. And then we developed a prototype plan to kind of prove out that architectural vision. Another big driver of this, right, was aligning with the Pangeo community and all the work that they've been doing. And so we wanted to give access to that in IUSE's regular day-to-day, things like Jupyter Notebooks, Xarray, Dask, et cetera, et cetera. And we also recognize a need to improve performance overall of data delivery. So looking at, what is IUSE, the kind of current state of data management. So this system that's drafted out here, we actually operate this in the cloud. So yes, it's in the cloud, but we're using not cloud native things. I'm sure people here are familiar with threads. That's what we're using for data distribution now. So to populate that, first of all, from all the regional associations, right, we have to go out to all these different websites and download data, right? And then we bring all that data into an S3 bucket and store a rolling 30-day window. This is, fairly expensive to store this each month. And then the problem with, hitting a lot of these websites, it's not event driven at all. You kind of have to guess that the data's there, and sometimes you'll access a forecast too late, and then, oh, it got deleted, it got overwritten by the next one. Things like that happen all the time, or you get behind on jobs, et cetera, et cetera. Second, operating threads in the cloud has been fairly expensive for us. We're not able to scale it horizontally, meaning like we can't run many different threads instances. So we have it on a large 128 gigabytes of memory machine, which is expensive. And then also because it is relying on kind of local disk access, we trick it into thinking our S3 bucket is a local disk. But then every time you do a read and list out your files, that costs you, cents per file. And that adds up to another big bill. Finally, then we put this NCWMS2 layer in front of threads. So that's kind of generating our map tiles for our front end visualization. And this pipeline has been quite a big bottleneck. So overall, right, there have been some advances toward cloud computing. It's been great through the NOAA Open Data Dissemination or the Big Data program that there's a lot of data out there now on the cloud providers. I'd say it's still not necessarily accessible, especially we've seen if you have a lot of GRIB or NetCDF, it's not necessarily, it's pretty slow to try to retrieve those natively. And then you kind of have to understand still how to get those files. You have to understand the time format that they're in or what instrument they're representing, et cetera, et cetera. Second, there are legacy server platforms, other than not scaling, which I mentioned, they're not able to support the new grids that are coming out. Here below, this is the Northern Gulf of Mexico operational forecast system. It's an unstructured grid. It's about 500,000 elements and 300,000 nodes, and that's to model finely along the coast. Threads is currently, we're not able to aggregate the files. It's challenging to understand this unstructured grid, and it just doesn't work. Finally, there's a lot of focus on copying files to the server paradigm with a lot of these different legacy systems, and that costs a lot of resources as you're moving these large forecast files throughout a pipeline. Whereas in the cloud, you bring everyone to your data. So to solve these challenges, we kind of did a two-step approach. So one of our first prototypes is just using this library called Kerchunk, which essentially allows you to generate a ZAR representation of your NetCDF or GRIB library. So that means that you don't have to modify your existing NetCDF or GRIB files. We saw that we were not going to be able to convince people to start pushing out native ZAR. So this instead, you can take that file, map it, and it generates a small metadata file, kind of representation there in that upper figure. So then you know where the chunks are for the data, and you're able to just grab those chunks that you want. You're also able to get more parallelism on S3 storage. And then because this is a forecast, right, we're continuously receiving new files. So we implemented this workflow system, which works by listening to the bucket events. So when new data gets uploaded to the node, we kick off some events, and then we execute this Kerchunk process, and then we save just that metadata. So we're not copying any data, so it's actually pretty small. And then when you access through that ZAR representation, you just get out the chunks you need. And the second piece of this is the aggregation piece. We also did this with Kerchunk. And you might be familiar with how forecasts work here on the right. So I won't go into it, but basically we create a model run, which is the hourly, or what the full run was, so that you're able to, when you load that in Xarray, view that as kind of one virtual file and go through it in your Python code. We did the same thing for the forecast model run collection, which is like the best time series. So you can see, okay, what was the best version of my forecast. We're currently doing that statically, so saving that metadata pre-computing and saving it, but there are kind of some other methodologies out there that we may want to try. For instance, virtually aggregating, so doing this on the fly as well. And then there's also some work, David Stubbe at Camu Energy, they're doing they're using the 3 years of her data to inform to do machine learning. And so he's actually putting all that in a database. So few interesting ideas out there for that. So that kind of helps. That helps a lot with the data analysis. So now when we're able to point at these czar collections, we can, you can go in your Jupyter notebook and now you have fast access to that data. But I think now, when we're talking about serving data products, most of the time, right, we're not looking at an entire forecast. We want to extract information out of that. And usually that's in the form of, viewing it on a web app, getting map tiles, doing some specific analysis in a geographic area of interest. And then of course, with the rise of maybe more autonomous agents, being able to handle more machine-to-machine queries. And so this, we've kind of jumped on the XPublish platform and we're actively developing it. So it's started by Joe Hammond, that's part of the Pangeo community. And we kind of took this actually during a code sprint and just kind of started hacking away and saying, is this something that we can do? Can we actually create an API to serve this type of data? So yeah, I did want to throw that in there, that we do have hackathons. Like right now it's every 2 years, but we hope to make it more frequently. But that's been an effective tool for us to come up with, get a bunch of developers in different communities together and just start brainstorming ideas. And this actually then took off and we kept building on it. So the idea of this is to have like a plugin based system, meaning we don't want a monolith where every time somebody wants something different, you have to check it into this big repository. Instead, we created like a plugin API. So as long as things are able to be read by this API, then if you need a certain feature that doesn't exist in XPublish yet, you code it up as a plugin. It's usually less than 50 lines of code. So made that integration pretty easy. And then you can run it. And this kind of assumes underlying, it loads the data into the Xarray data model. So then you also have access to the ecosystem of tools that are all out there in open source. And so you can do anything then in Xarray that you could, like in a notebook, you can now do this behind a web service. So you see here, I took that same forecast. We're able to render that fairly quickly. And so we support both regular and unstructured grids. And we're actually able to pull and map this data at about the same time as the legacy systems, which have to pre-compute and regrid before they're able to show you any data. So we're going to continue to working on this. Our next code sprint is actually coming up in a month, and we're going to be improving the performance, reliability, and making it easier for people to host and deploy this. So now I'm going to show those are kind of our main ideas, technologies. So what are we doing with them, and kind of give you ideas where they might fit into your workflow. So these are all open source. So the first are RPS's kind of flagship product, our Oceans Map. You think about it as it's a real-time mapping platform on the web, such as like Windy or Weather Underground, but specifically focused on using NOAA models for mid-ocean operations. And then we create custom applications or implementations based on the client's use case. So if you're more into oil spill monitoring, or if you want a platform for data sharing, we create different portals based on that. But in the back end, it's all the all the same software stack. And it's actually using that Threads NCWMS stack now. So one of our big plans, right, is to upgrade the back end of this. And specifically, co-ops, which is the kind of operational group for IUSE, they're interested in taking Ocean's Map and will use the upgraded XPublish as the backend. And we've already been testing this. We've seen great performance improvements for serving this kind of data. So our next application, the NOAA Coastal Ocean Reanalysis. This is a 40 years of hourly water level data. And here we're supporting scientists, letting them do better data analysis by, we applied the Kerchunk methodology to this very large data set. We set up a Nabari, which it's like a scaled up Jupyter hub, so that they can log in, run Jupyter notebooks, and start interacting with this reanalysis data. So before it was unoptimized, the scientists were unable to do a lot of these operations within a reasonable amount of time or at all. And now by applying Kerchunk, we can access this data in a matter of seconds. 1 month time series takes 2 seconds. All the time series takes 3 minutes, or you want the daily max, that's 6 seconds, whereas the job didn't finish before we did this. And then final application, this is something we're actively working on, subsetting model results in the cloud. So there's a forecast called GNOME. It's an oil spill model. Requires forcing data from these two models, NGOFS2 and WCOFS. And the current workflow is that they need to download those full data sets in order to initialize the model. Of course, because this is for hazardous spills, timeliness is important, and the downloading is currently one of the bottlenecks. And so again, applying Kerchunk to these forecasts, we kind of do that for everything now. Every time we get a project, like let's just apply Kerchunk. It's a no-brainer, so that we can quickly access that data from the cloud. And then we are adding to our XPublish, creating an API to do the subsetting. And we are now able, so first of all, this Kerchunk process is very quick. So as soon as the model data is up there, we kick off that, it's within minutes. And then the subsetting, again, depending on what you want, it's very quick, it's within seconds. So still actively developing, still haven't even done a lot of explicit optimization. And so this will enable people to basically hit an API endpoint, grab the subset of data, rather than having to download an entire forecast. So overall, we're, RPS and IUSE are very invested in the delivery of cloud native data. We really like these workflows. We are doing this all in an open source community. And I think the big thing about XPublish and how NOAA tends to work is, you often have like 1 or 2 software developers on all these teams, but you're all kind of trying to do the same thing. So XPublish has been a good platform for us to kind of share those ideas and keep, we're doing the subsetting, but somebody else is doing like open DAP integration. So I think this is really accelerating our workflow. And like I said, the code sprint was very helpful in creating these ideas, and we're going to be having another one where we'll be updating this stuff. It still is definitely a prototype, but because I think we have a lot of commonalities between the atmospheric and ocean communities, I'd love to see more of the atmospheric community also contributing or joining in on our meetings, as I think this is a common platform that can serve both of us. So with that, if we have more time, I can do some demos or do questions. Thanks.
Yeah, so we have about 6 minutes. So if you want to run through a short demo and people can think about questions while you do that, I think that's a good plan.
All right. Good, my sharing worked. So yeah, so to kind of give an idea of, you know, this is our prototype I was talking about. So this is a kind of a mapping layer with XPublish in the background. We have all these different data sets loaded. This is that very large gridded data set unstructured grid I was talking about. And so we're able to really pull that data back pretty quickly. And so under the hood of this is XPublish, essentially. It's a collection of APIs. And so you're able to see kind of the different operations. And every implementation doesn't have to have all of these capabilities. We, understand, different people may be hosting this and want different capabilities. But it basically gives you a web API where you're able to access whatever data sets you have loaded into here. So the connection is that this data is been chunked, and then XPublish references that, and then you pull it out through these API endpoints. And then to talk about Oceans Map a little. So this is an example of one of our dashboards for offshore wind developers. So we're showing, not able to scroll down. We're showing the current winds, and then we have different thresholds defined. And so then you can see throughout the forecast, where it's, good, impactful or not. You can see wind direction to kind of get some ideas. So again, these are the types of data that we are trying to pull out of XPublish. And I can't. There we go. Losing screen real estate. This is another view of Oceans Map. Another view of Oceans Map showing the GFS winds and comparing that against observations from a specific buoy here in Rhode Island. Yeah, I think that's about it, unless someone wants to see something specific.
All right, do we have any questions in the room or online? Please.
So if I got the picture right, you've got these files that you collect from, they're all disparate formats, and they could probably be pretty big files and hard to manage, because of their size. And you're using this chunk facility to break it into smaller pieces, not necessarily the file, but being able to index into the file, right? And so have you found that there's kind of a sweet spot or something that about the size of the chunks that you create? Does it tend to go towards that, or is it just pretty much case by case basis for that?
Yeah, there is a sweet spot. It does depend a little bit what you do, but we've also found that it actually doesn't matter that much. Just doing that chunking greatly improves the performance. I know that if you're doing Dask, they kind of recommend around the 100 megabyte chunk size, but I don't think we've paid a ton. Obviously too small a chunks and too big a data set, then it's you're going to overwhelm and have like too many jobs going, and then too large, you're just going slow. So yeah, around that 100 megabyte range seems fine, but just chunking in general will greatly improve the performance.
Yeah, so you're saying a bigger factor really is just breaking it up. So you don't load all this extraneous data that you don't need.
Right.
Yeah, okay, great, thank you.
All right, thank you. Any questions online? All right. Yeah, if there are no other questions in here, then I think we'll call this a morning session. Thanks, Jonathan.
Thank you.
So yeah, it's time for lunch. I think today is going to be the one guaranteed nice day outside, so would encourage you to take advantage. And yeah, lunch should be set up out there. We will return in here at 1 p.m. Oh, Tasia has an announcement.
Hello, thank you. So we are going to have an extended lunch today. It's going to be 12 to 1:30. So enjoy that. There for in-person speakers or in-person participants, there is food out here. And I just want to do a quick reminder. If you said you had allergies or needed any accommodations food-wise, just keep that in mind. There are labeled bowls for people who requested it. And if you have any questions about that, let me know.
All right, thanks, Tasia. So yeah, we'll meet back in here and online at 1:30 Mountain Time. See you then.
Good afternoon. So I think my voice is up, right? We have a slight change to our schedule in the afternoon. It will be starting at 1:30 p.m. If you haven't heard this announcement in the morning, so just, just let you know. There is one canceled talk, and because of that, we are extending the lunch time to 1:30 p.m. Yes, you.
Feel free to use these mics. Okay. So right now. No, it does.
So, sorry to interrupt your bonus time and lunch, but just wanted to make a quick announcement slash request. So Tasia, who again is like the backbone of this conference, she wants to do a group photo. And since we have an extra long lunch, we figured this would be a good time to do it. So if everybody's okay with that and willing, maybe you could just head out to the atrium and we'll take like a quick picture or two of the group, for advertising the conference. So if you can go do that now, that would be awesome. Thanks.
Okay, almost, it shouldn't be any. You never know.
Good afternoon, everyone. My name is Orhan Eroglu, and I am a software engineer at NCAR Sizzle. With the afternoon session, I will be helping moderate these talks. We will have 3 talks today in the afternoon one, and I hope before everything, we all had a refreshing lunchtime with the food and conversation. So, as you all may know from the morning session, we have one talk canceled, and we will be starting with the first talk at 1:30 p.m. Christina, Holt, and Paul Madden are with us. Christina, Paul, would you like to say hi to the audience?
Hello.
Hello. Thank you so much for being with us, and yeah, the stage is yours. Please take it away.
Thank you. Paul, were you going to share these slides?
Yeah, you want to step me through them?
That would be perfect.
I can do that.
That went really quickly. In reverse, that's fun. Hi, everybody. I'm excited that we gave you a little extra time for lunch today, a little time in the room there. I'm Christina Holt, and Paul Madden here is my co-presenter. We are representing a larger team. Everybody's listed here on the first slide, and we're all from different organizations coming together as one team. Next slide, Paul. We operate under the unified framework system as an agile team that works with EPIC. EPIC is the Earth Prediction Innovation Center, and they use the scaled agile framework to operate several different teams. And ours is the one responsible for contributing to the unification of workflows across the UFS. We really do welcome any contributors with different objectives to achieve a common goal. And right now, our current team is comprised of staff from Ceres and NOAA GSL, where we have funding from the Joint Technology Transfer Initiative and the Software Engineering for Novel Architectures programs. And then our EPIC staff comes to us from Raytheon and Element 84, a couple private companies that are operated under the EPIC contract. Next slide, please. We have several goals here on the team. And of course, the first one is unification, where we've defined that as multiple applications using the same tools to perform the same tasks. Now, we want to make that process as easy as possible by flattening the learning curve to get what you need out of a UFS application. We are empowering scientists to do the experiments that they need to be doing. But with a flexible workflow, they aren't limited to just what already exists. We also plan to facilitate research to operations and operations to research, because configuring any of these different systems is just a matter of running the same components and using the same languages and infrastructure to get the same types of results out of that. Next slide, please. This is not a new concept. We've been talking about this for several years now. And in fact, back in 2021, Hendrik Tolman presented this slide, kind of telling us his idea of what a unified workflow would look like, where really he was just seeing it as a library or a set of components here that will help us to standardize over the runtime configuration, the runtime scripts, and then be able to use the same components here at the top level that everybody is already using, but be able to work with them very similarly in every research application. So our tool set now, next slide, please, is a Python package that provides that library that he envisioned several years ago now. It has a command line tool set and a Python API that perform common workflow tasks and then drive the UFS specific components like the forecast models, post-processing, verification, and others. We publish each of our releases to an Anaconda channel named UFS Community so that it's easy to install for any of our folks using Conda, but we also support a pip installation from source. We're planning to integrate these tools with multiple UFS applications, and we're currently working with the Short Range Weather app, as well as a land DA application that's a standalone and one of the earliest JEDI-based land cycling community-supported systems that we have. Next slide. Now, our tools are currently on version 2.1.1. today. Wait just a little while and it's probably going to increase. But you can install that with Conda pretty easily with just the standard Conda install, giving it that UFS community channel flag. And what you get with that is a UW tool that requires a mode and an action. And I'll explain those on the next slide with a help flag. You also have an API that allows you to use the tool set inside your pre-existing Python scripts. By going in both of these directions, we hope that we've really served the community who have already moved to Python, as well as those who are still using Bash for a lot of their use cases. We serve our code out on GitHub like most other folks, and it's just named UW Tools. You can get to it from this QR code, and we have pretty extensive documentation on Read the Docs. Next slide, please. So here I'm showing that we have, like I mentioned, the UW interface on the command line. Paul, I'm sorry, this one is automated. So one more click. And then one more. That next column here is going to give you a variety of different modes that you can act on. In the third column, with one more click, we can see that you have a variety of different actions you can take. So here you might be working with a configuration file that you want to compare two things. I'll show you an example in the next slide, but then we have drivers for like FV3 or UPP or a handful of others currently, or you can work with templates. I'll show you a couple of those a little bit later, but then one more click gets us to that help flag that's available at every level, so that you know what should come next in the progression of building up the full command. Next slide, please. So I'm going to start with the config tool, and this is one of our very generic tools that allow you to do a lot of different things. It's maybe our most powerful configuration management tool at this point. So you can compare, transform, modify, and validate all under this UW config level. And we support key value configurations for a lot of the standard formats that we use here. So YAML, Fortran nameless, INI, and bash. Next slide. The config compare tool is maybe one of my favorites, and if any of you have tried to compare two scientist nameless in the past using the Linux diff tool, you'll understand my pain. Here, you're just putting in two different nameless or any of those supported formats that I was just mentioning and getting out a nice annotated difference between the two so that you can really see what differences exist. Next slide. The config realize is really an important tool at the app level, where this input file on the top represents something you might see saved and in an application where you would keep defaults. And then you may also see that there's some derived information here, like the number of nodes to run the forecast or the processors per node really is going to depend on thread count, for example, and a variety of other factors. So here we've given users the ability to set their defaults, provide derived information right here in a YAML file or any of the other supported formats, and then apply an additional user configuration on top of that. So in this case, a user wants to change the number of threads to 4. They can do that really easily with just a small additional amount of information, and then you use the tool and get the output file here in the bottom right, where all of the pieces of information that used thread count is going to be updated. Next slide, please. We also support a template tool that leverages Jinja for a Turing-complete templating language, where we often see that we just have really simple templating options where you just plug in values. But if you go to the next slide, I think we'll see an example where we have really simplified the way that you can interact with Jinja templates, and also given you that Linux piping ability with our template render tool. So here I'm just doing a very basic example of using pipes, which is supported in a variety of our different tools for providing input. And then setting an environment variable cycle to manipulate it within the template to check to see if strings are sliced appropriately. One additional feature of Jinja is that it will tell you which values are needed in this very basic template. It's not so required here on this very simple example, but it does help when you get longer ones. Next slide, please. So this one may go on for, I don't know, 1,000 lines or something, and you need to know what all the values are that you need to provide here, and that is where it comes in handy. And also you have the introduction that we haven't necessarily seen before of having control structures that you can include here. So for in-hours forecast, we can make some choices based on cycle information about how long the forecast should be at various different cycles. Next slide, please. I'm going to stop there with our generic overview of tools and pass it over to Paul for the graph-oriented drivers, which I think is the niftiest part of our tool set.
Thanks, Christina. So just defining a couple of terms. First of all, drivers. This is the term that we're using to refer to code that's responsible for configuring and executing a number of numerical weather prediction component programs. So an NWP workflow might comprise some prep tasks, forecast model runs, some post-processing tasks. Each of those programs might have its own requirements for run directory structure, configuration files in various languages from YAML to XML to Fortran nameless, a script to run all of that together and set environment variables, et cetera. So by providing a structured YAML config that drives these tools and does it in a consistent way across a variety of tools, I think we're providing a service to our community. Graph-oriented means the usual thing. As you see on the left, we've got the diagram here of a graph where nodes represent tasks, and more specifically, they represent the outputs of those tasks, the targets or assets that those tasks create, some sort of external observable state. And the edges represent dependencies between those tasks, both in terms of data flow and execution order. This concept, directed acyclic graphs, this is the core principle behind kind of workflow management engines that we see more and more of, and lots of the work that we do. We can execute the entire graph. In this case, run is the most general node in this graph. And by asking for a run, it implies the execution of all of the tasks it depends on, which are a provisioned run directory, which then contains a run script, some data files, a name list file. And then each of those tasks has a common dependency on some kind of run directory that those files need to exist in. So we could, for example, run UW ungrib run, where ungrib is a data preparation utility for the WRF and MPAS models. And we would get the complete execution of this graph and the output that that run implies. But one of the nice properties of this graph execution technology is that you can enter the graph at any point and obtain just a subset of the total functionality. So in the second line in the green box, for example, you see that we can just ask for the name list file from this graph, and we would get the name list file in the run directory that it requires, and nothing else would be done there. This is useful in lots of different use cases to get, for example, the assets that you're going to need for a run, maybe manually configure them or do other things with them without actually forcing the run to execute. Nothing new here. If you've ever written a make file, you're familiar with these concepts. If not in name, then at least in principle. Make may not talk about graphs and nodes and edges per se, but it certainly implies directed acyclic graph. For example, in the code box on the upper right, we want to produce a program called foo. That's the target or the output of this process. It has a requirement to the right of the colon on one source file and two object files. And then below that, there is an imperative piece of code that's responsible for creating the output given the inputs. It's also a recursive definition because the object files themselves have their own recipes just below that talk about how to get those .o files from the .c files, again, with an imperative command that creates those. Of course, we wouldn't write it like the upper right. We'd use the great concise makefile syntax below. Now, make, though, is very literal about files and timestamps. Those are the core principles of make, and they're not really general enough or even abstract enough for the full variety of things we want to do in NWP workflows. So there are more powerful tools. For example, the Luigi Workflow Manager, published by Spotify, provides the same concepts as make, but in a more abstract way, giving us the power of Python to do anything we want in terms of defining what outputs look like, what prerequisite criteria look like, et cetera. In this case, Luigi requires that tasks be represented as Python classes that expose three methods, three key methods. One of them is the output method that declares what it is that this task creates. And then that can be introspected to see if it is already available or ready in some sense that's appropriate to that kind of asset. If it is, then the task doesn't need to do anything else. You're done. The task is complete if its output exists. If not, Luigi can then look at the requires method to find out which tasks this task depends on. And only if all of their outputs are ready, then it can move on to the run method, which is the imperative part of the recipe that creates the output that this task is responsible for. So again, these are the same concepts that we see in make, but they can be much more abstract. For example, our target doesn't just have to be a file. It could be something like a response from a REST API or even something as abstract as a specific time of day having been met. You could have one task require a task that says, it's after 12 UTC, and that task would be blocked on its execution until that time of day is met. So a lot more power than we have with Make. So frameworks like this, and then even more complex ones like, for example, Apache Airflow, or things we have in NWP like EC Flow or Rakoto, they're great, but they're still maybe more complex than we would like in some applications. In particular, I would call this kind of an in the large workflow management. So you're really here running Luigi, and then Luigi is running some of your code for you. Luigi also has a lot of dependency packages. And what we would like to do is be able to use this kind of technology inside a command line tool like UW Tools and have our code be the primary actor, but still have access to these techniques. So in UW Tools, what we are doing is using decorated Python functions that yield values that then guide the driver behavior. On the left, you'll see a slightly simplified, but not really unrealistically simple version of a decorated task function. The numbered lines are the key part here. The function is required to yield 3 values to the framework library. The first is a name, a description of the task that can then be used in logging by the framework. The second is the asset or some number of assets that this task is responsible for making ready in some sense appropriate to those assets. And it's composed of, first of all, a reference to the asset itself, which another task that depends on this one would be able to use to get access to that task. That sounds abstract, but think of it as just a path to a file in the file system in the simplest case. But it could also be something like a URL or anything else that allowed another task to access this resource. And the second item in the asset is a readiness function that the framework can execute to decide if this asset is already ready. If it is, then the framework doesn't have to go any further. It doesn't have to move on to steps 3 or 4. This task is already complete. There's nothing to do. If it's not, though, then the task can move on to step 3, where the function yields to the framework 0 or more tasks that this task depends on. Only if the assets returned by those tasks are ready, then the framework can move on to the 4th step, which is the execution of imperative code that creates the asset that this task is responsible for. In this case, it's a call to a function, but this could be any number of executable statements that would do the core work of this task. One thing that you can notice here is the lack of error handling code, logging, conditional statements, et cetera. This kind of boilerplate that we usually have to write in bash scripts, et cetera, is handled by the framework. And you'll see some examples of that as we go on. So using these techniques, we get a number of nice properties. One of them I'll call iteration is the fact that this task graph can be repeatedly executed, making partial progress potentially each time it's executed toward its complete and final state. It's not a problem if you can't do everything during the first iteration. Maybe you're waiting for some external file to become available. And when that file becomes available, you can make more progress then. But you can do as much work as you can at any given time and then hopefully eventually complete all of the work. Composition, one task graph can be wired up to another one by the second declaring the first as a dependency. So for example, if we had a prep task whose outputs are, for example, initial conditions for a forecast model, we might have a second task graph, which is driving the forecast model itself. And all it has to do is depend on the run task of the prep graph to obtain those initial conditions. So you could wire those up, execute the entire workflow, and you would make all the progress you could as prerequisites became available. Selective execution, we've already seen. We can ask for just subgraphs to be executed, any particular part that we want. We can cherry pick that. Toil reduction, all the logging, error checking, conditional statements, and so that you would normally have to write. Most of that is handled by the framework. We can augment that if we like, but the core requirements are handled for us by the framework. Idempotence, once work is done, it doesn't have to be repeated, and we don't have to, again, write conditional checks to avoid clobbering files that we created in a previous iteration. Because of that readiness function that tasks attach to their assets, the framework can see if that work has already been done, and then nothing needs to be done after that. On the flip side, we have self-healing. If some asset no longer exists or is not ready in whatever sense that's defined for that asset, then the framework will re-execute the imperative part of the code and recreate that asset for us. In addition to the task decorator, there are two other decorators. One of them is just noted in the footnote as @external. That allows us to modify or model external assets that just have to exist. They're not under the control of the framework. You can think of them similarly to source files in a makefile. They just have to exist. The makefile doesn't create the sources for you. It consumes them and requires them. So we can model that with this external decorator. And then there's the, as shown in the upper text box here, tasks plural decorator, which defines a sort of container task whose readiness is defined as the readiness of all of its contained tasks. So this task is complete when all of its contained tasks are complete. It delegates execution, flow of control to those subtasks. So in this case, we have something defined called a provisioned run directory, which is meant to contain all of the items we need for a run to happen without actually executing the run. And in the case of this prep utility that we're playing with here, we require some grib files, a nameless file, a run script file, and a vtable file in the run directory. That's how this task is defined. So if we run this with UW tools, run UW ungrib provisioned run directory, that's the name of the task. We provide some cycle information and then a YAML config file that provides information that will help guide the setup of the run directory. For example, the contents of the nameless file would be defined there. Well, the first thing we can note is in green, added to this slide. It's unfortunately not currently part of the tool colored output. It would be nice though. The three green lines show that 3 of the 4 files that need to be in the run directory, their prerequisites were satisfied. We could create those files and those are ready. We won't have to redo that work. Unfortunately, we do require a 0-hour forecast file from the GFS. And at this moment, we see on the 6th line, that's the first warning line, we see that this is an external asset. We can't create it. We just have to wait for it to exist. So this task, gribfile.aaa, which was meant to create a symlink in our run directory to that GFS file, that's left in a pending state. We can't complete that at this time. And then on the last line of output, we see that the overall provision run directory task is also in the pending state after this execution because it could only complete 3 of its 4 tasks. All of this logging that we're getting is just coming from the name list. It's telling us what it's doing step by step, and we see what the state of various tasks are after execution. So of those benefits that we mentioned, a few of them are on display here. Iteration, we were able to make at least partial, if not complete progress. Composition, we know that provisioned run directory is composed of several other tasks, the nameless task, the run script task, etc. Selective execution, we also know that provisioned run directory is the dependency of the run task, but we don't have to perform a complete run. We can just get this provisioned run directory by asking for it directly. And then toil reduction, you saw how concise these kinds of task functions can be. We don't have to write error handling, logging, et cetera. We get nice timestamps, a nice trace of our execution. So after the first invocation, we have our run directory with 3 of the 4 files. Now let's say that this GFS file becomes available. If we rerun exactly the same command, we only need to do the work that was left undone in the previous iteration, much like a makefile would make further progress if some extra prerequisites became available. And then in this case, the final state of the provisioned run directory task is ready. It's done all of the work that it needs to do. Once again, we see iteration and idempotence. You don't see any work related to the nameless file, the run script, et cetera. That was handled in the previous iteration. We don't need to revisit that. So at the end of this invocation, we have our complete run directory with all 4 expected files. If we rerun our driver at this point, no harm done. All the work is done. It's in its final state. This is a steady state for this graph. Unless, for example, we remove one of the files from that directory. So this is a case of an asset now ceasing to be ready. That's detected by the driver, and then it recreates that file. And once again, we're in the final ready state. It might be that between those invocations, we changed our config.yaml file, maybe the name list file didn't have the content that we expected, and we realized like, oh, we need to fix something in the config, delete the file, rerun the driver, and everything is brought up to date into the right state. And finally, since this provisioned run directory, excuse me, was the dependency of the run task, we can sort of upgrade our invocation now to ask for the complete run of this component. So we'd say UW ungrib run, same cycle information, same config file. All of the provisioned run directory work was already complete. So all we have to do is actually execute the program, and we get, as shown in the lower box, the initial conditions file that we expect, and the final state of our entire workflow is ready. So that's this in a nutshell. Yeah, I want to say I was gratified to hear Alicia's comments in the keynote this morning about simple ideas being not necessarily something you want to stand up and present at supercomputing or even at this conference. And I feel like this falls into that category. It's a simple concept, but it's also powerful, and I don't see it used in as many places as I'd like to see it used. We're finding that we can iterate more quickly on these drivers. We can produce them more consistently with a more consistent and good user experience using these techniques. So, adopting a fairly simple idea, but well executed and doing it a lot, you can pick up steam and get a lot done that way. So thanks for that. I'm going to let Christina speak now for the final comments.
Sure thing. I just want to iterate that UW Tools is a Python package that you can go and should go install today in any of your Conda packages or Conda environments. We're trying to design tools here that will help scientists be productive and increase the automation of common tasks, which we talked a lot about this morning. The graph-oriented drivers offer that more flexible opportunity than many of the solutions that are out there that are often hard-coded, procedural, and become brittle over time. And then I think this is really going to help with hierarchical testing too, giving researchers tools that they can do a lot with in their individual run directories and that sort of thing. Next slide, please. I'm just going to leave you here with some upcoming plans that we have. Note that if you go to our landing page in our Read the Docs, you'll see all of the currently available tools and drivers that we have, and we plan to document a little bit better in a similar way all of our upcoming plans so that you can always stay up to date with us here. And then that last slide here is acknowledgements, and I think I'll call it done there if we have time for a quick question.
Thank you so much. So we can see. We can see if we have any questions from the room or from Slido.
Yeah.
Ryan, yeah, go ahead.
Yeah, let's quick question. So I feel like with tools like this that sort of sit on top of other tools and abstract some of the complexity away for the end user, where I find that can cause trouble is if something in that interface or if the underlying tool runs into a problem, and then the user who maybe doesn't have a ton of experience with that underlying tool, like say the workflow manager, then they're not prepared to debug that problem. So have you thought about how to support the user when they're using your tools and they run into a situation like that?
This is something that's starting to come up a little bit as we've had a few releases now and people are starting to use the tools. I think that the level of logging that we're getting is going to be new to folks, and so it's going to take a little bit of additional hand-holding, I'd say. In that realm, we are hoping to generate some more interactive documentation to help onboard new users a little bit better than written documentation, which is personally not my favorite way to learn a new tool, although I know other people do actually read the docs. But I think the other thing is that we're trying to release these as quickly and often as possible so that we can get that feedback. And we're really aiming at a few early adopters of different apps first so that we can start to help with that process and that learning curve.
All right, thanks.
Thank you. Any more questions? If not, I think this marks our end of first part of this session, and we can do another 30-minute break. So Christina, Paul, thank you so much one more time. And I think we can. Thank you. And let's come back at 2:30 for the second part of this session. Thanks so much.
Thank you. I don't know how it's used. Yeah, right. Yeah.
Then you, yeah.
This does everything.
Yeah, this does everything. Okay. And you don't even have any, keyboard. Okay. And if you need anything, I will start the button. So I give it a try, yeah. Yeah. Yeah.
Okay, hello everyone, one more time. It's almost 2:30 p.m. We can, I think, get started with the next talk, which is going to be given by Steve in the room. So, Steve, yeah, please. And just a heads up, once we wrap up Steve's talk with everything else, including the Q&A, I will need to head out and Brian is going to be taking over the rest of today. So, Steve, yeah, please.
Thank you. And my name is Stephen Herbener. I'm a software engineer and I work at UCAR in an organization called JCSDA. That's the Joint Center for Satellite Data Assimilation. And this is a development, one of the major projects we have is development of a data assimilation weather forecasting system. So what I wanted to talk about today is how the infrastructure that we lay the foundation for this system and the importance that it has and the impact that it has. So I have put on here the people who are on the infrastructure team, my teammates. But I also wanted to point out that the whole JCSDA core team at UCAR and many contributions from the JCSDA partners that actually put this whole JEDI-Skylab system together. So a little bit of background. We're experiencing an era of rapid development of innovative techniques, such as processing big data and machine learning and things like that, that are being introduced into the weather forecasting operations. And this necessitates the streamlining of the transition of research to operations. And one of the challenges that comes up with that is to effectively and efficiently select and move promising research results into operational weather prediction systems. So, sorry. The Joint Center for Satellite Data Assimilation is an interagency partnership, and we're working to become a world leader in applying satellite data and research to operational goals in environmental analysis and prediction. So this is just kind of depicting the partners that we work with, and wanted to point out strongly that it's a very highly collaborative effort between us and our partners. Okay, so this diagram depicts roles that this Skylab system plays. So Skylab is a test bed for trying out new ideas and then getting them transitioned into operational modes. And we see these three roles that the test bed takes on. So I'll start with the one at the top, this one up here. It's called Skylab Large. And what that does is allow you to run high resolution model configurations with large representational observation data sets. And this enables kind of the real world system hardening and course scientific quality assurance, which in turn enables the R2O transition to complete. So this is kind of the end of the line when we're ready to deliver the new feature into operations. And then down here, there it goes. Down here in the blue, this is the low resolution model, Skylab Small. And this is very useful for getting started into this R2O pipeline. It's a quick running tutorials that get the concept across without long run times, and you can do rapid design cycles so that you can do the more strongly developmental phase of the feature that you're trying to develop. And then this yellow box on the lower right is medium, and that kind of serves as a bridge between the entry point into the R2O flow in the small system and the entry into the the delivery of the R2 or feature into the operational system. So a little bit more about some of the details inside of JEDI-Skylab. The main transition that you're trying to do here is ingest a bunch of observation data that's depicted by these pictures here, and then use those data in a forecasting system, and then dump out some diagnostics and things so that you can monitor what's going on with your system and keep it in a stable state, and to also see which observations are doing more work or having more impact and things like that. And you can fine tune the system and get it optimally configured. So in this ingest part, there's two systems within JEDI called YODA and R2D2. And these are the things that collect up and deliver observational data to the system. And then they put it into a common format so that the system can use it, and it's not so complicated because these pieces over here, they come in very disparate file formats and layouts and file types and things. And we're trying to unify it into one format. And then once the next piece here is the use part, the forecasting system, and this is the EWOC system. And the EWOC system is a workflow manager that's very much like the prior presentation that we saw. It's generic in nature, and what we have it wired up to now is the system from ECMWF called ECFlow, but we're also planning on putting in Silk and some other workflow managers underneath it. And then over on the diagnostics side, we're developing Python kits to be able to do plotting and to do this little picture here is called a scorecard, and it tells you how well your forecasting system is doing. You can kind of rate it and score it and see if it's doing a good job of predicting. So once you get the system all put together, one of the features of JEDI is that on the side, the left side over here, it's easy to add in new observation types, like a new instrument shows up and you write a new converter for it to get it into the format that YODA can read in and that R2D2 can manage. So there's an aspect of being able to quickly add a new instrument, and say you just developed a way to process that instrument. You can go and just write the converter to get it in, and you can take advantage of all the models that are already wired into the system, and you can start trying it out in an actual weather system. You don't have to develop all these other pieces. And the same thing happens on the model side. It's not really shown in this diagram, but you have the same kind of feature where models are developed externally, and there's an interface that you can attach it to the piece that runs the forecasting. And you have the same kind of aspect to it. If you have a new model that you want to try out, you can take this set of observations that already exist and all the algorithms and things that are in the system, attach the model, get it all running, and you don't have to worry about developing all those other pieces of the forecast system. And what this testbed does, it kind of boils down to this piece here where you have configuration files, and you can configure this to run in these different modes, these roles that I put on the previous slide, like the large and medium and small. And you can do it for a atmospheric weather system or a land system. That'd be like modeling the way water drains off through a river system and predicting floods and things like that, or a marine system or aerosols and these different pieces. And all you have to do is just change this configuration. All the pieces over here are generic, and you just put in one of the configurations and you're in these different modes and everything. And it makes it very easy to try out a lot of different things. And we are working on a concept now or we take these configurations and we wire them up so that they look very similar to the operational flows that we're targeting with the new features. So we're calling this a proxy application. So instead of playing around with different models and observations, what we do is put a representative set of the types of observations that are in an operational flow and use the same model that's in it. And we can put down like a Skylab that looks like EMC operational mode. And what this does is give a person who's developing a piece that they want to contribute, they have an environment that looks an awful lot like the target system that they're going after. And that helps facilitate this whole transition from research to operations. So when it gets all put together, this is just a diagram that kind of depicts this whole JEDI-Skylab testbed system. So here in the middle, we have the JEDI forecasting system, and around it are depictions of the different kinds of models, Earth system models that can be attached to it, constituents, aerosols, atmosphere, ocean, etc. And then in the outer band are different representations of the observations that can be ingested into it. So you have various satellite, microwave and infrared and visible ranges, and there's several ocean-oriented SSTs and sea ice and soil moisture for land and snow depth for land and all these systems put together to create this test bed. And I want to point out too, at this point, this is the result of a very highly collaborative effort that's done with the JCSDA core team and all the partner organizations that we work with. And this is to the credit of all these people involved. So I want to dive down now a little bit into the infrastructure. The other piece of this talk is about how the infrastructure kind of lays a nice foundation for all of this to be able to function efficiently. So in the infrastructure, we have this little star diagram here that depicts different aspects of the infrastructure. So there's 6 of them listed here. The software environment is handled by a feature called spack-stack, and I'll talk a little bit about these different pieces in the remainder of the talk. And the testing and the CI/CD, the continuous integration and continuous delivery aspects of it are implemented with GitHub and CodeCov and AWS pieces. This R2D2 and Yoda are kind of combined together to provide observational data to the and access to that data. The cloud administration is in 2 primary pieces right now, AWS and the NOAA Parallel Works. That is getting expanded. And then GitHub administration, we're using this thing called Terraform to do that. And then the workflow testbed is the EWOC system that I mentioned before. And this infrastructure is paired with an agile development methodology to get very efficient development design cycles. So for the software environments, spack-stack is an interagency collaboration to provide unified software environments. So this is talking about the software stack or the third-party libraries that are all used that we build our code on to. So you build this thing once on an HPC system or whatever, you install it, and then you can do your development work pointing to these libraries and things. And in this picture here, you can see that developers and users can use this alike, and just people who are using it, can all use this same software stack that's been built. And one of the interesting features about this, we didn't have the ability to use containers everywhere. Some of the platforms that we were targeting didn't allow that. in that. So we kind of bit this bullet and went to spack-stack and we build everything in the native environment on each of the HPC platforms and laptops and workstations. And it's really, spack-stack and SPAC have really been great in getting that task accomplished. And also Alex Richert will be giving a talk right after mine, and he's going to go over more of the details of spack-stack. So in testing and CI/CD, we're kind of at a point where it's a big CI, continuous integration, and kind of a little CD right now, the continuous delivery, but we're working on that. That's part of the push that we have. And we're doing unit and integration level testing is triggered with every commit push to an open pull request. And you can kind of see a report that you get from GitHub after running these tests. And then we're using this thing called C- to publicly display test results. So that way we can avoid having to give everybody accounts on AWS or wherever the test results are getting stored. And then the data store, as I mentioned before, is implemented with these two systems, R2D2 and YODA. And what we are accomplishing with that is getting findable, accessible, interoperable, and reusable data, or the FAIR system. And the R2D2 system is a MySQL database that manages all the metadata about the files. So it's keeping track of what's in the files, the time windows that these observations are between, and the different instruments and providers that they come from, as well as managing all the background information and the files that come out of the model runs. And that kind of covers the findable and accessible pieces of FAIR. And then YODA is a file IO and a memory store that's within the JEDI system that provides the ability to ingest data. And what it does is it can take different file formats and everything, puts it into kind of a unified memory image of it, and gives efficient access for the consumers of that in the forecasting system. So it kind of provides the interoperable and reusable aspects of the data. And then cloud administration, as I had mentioned before, we're doing AWS, and we have EC2 instances and AMIs and that kind of level of capability. And then we're also using NOAA ParallelWorks, and this is a manager of NOAA cloud resources, and they come from various sources. And we are trying to expand this so that we can cover more things like Google and Azure. And then GitHub administration, this tool has been extremely useful for us. It's called Terraform. And basically what it does is it takes this big master configuration file and then configures all your repositories according to that file. So what we were doing before was just manually running around and setting permissions and access and controls and branch protection rules and all these different things that you have in GitHub. And it was a very messy process, no consistency and stuff. And now Terraform has enabled us to do everything in a nice, consistent manner. If we ever decide we want to change something, you just go change the configuration, hit the button, and it goes and updates all the repository settings. And it's really a great tool. And then the workflow and the testbed is the EWOC system that I mentioned before. And I had mentioned that it had this EC flow workflow engine underneath it. But it also runs R2D2 and the YODA systems to get the data, and it runs JEDI to do the forecasting, and it runs the diagnostics, and it sets it all up. And this is just a panel that kind of shows what EC flow UI looks like. This is a monitoring device that lets you see where you are in your experiment that you're running. And I did want to point out that the EWOC development is primarily led by another team besides the infrastructure team in JEDI called the algorithms team. but we contribute to it with the R2D2 and the YODA pieces. So I wanted to give an example of maybe how this whole thing works and kind of provides some flexibility and productivity enhancements here. So one of the big projects that we're working on for this next year is to introduce this feature called continuous DA. And DA means data assimilation, so continuous data assimilation. So in the current system, we usually set up a scheme where at UTC times 0Z, 6Z, 12Z, 18Z, we do a forecast. And if you take a look at one of these forecasts, you have an upfront process in the blue here that's the ingest of the data, the observational data, and then filtering out bad data points and QC checks and various things. You get it all prepared and then you hand it off to the forecast system, which is more of the time here. But one of the issues that happens is as you're going through this forecast, there's more observational data that becomes available. So what we want to do is at distinct points in this algorithm here, we want to be able to take a look and see if new observation data has shown up, and if so, then ingest it and include it in the subsequent running of this forecast. So this development of this continuous DA will impact probably 4 or 5 code repositories that we have and require expertise from different areas of JEDI to get it completed. There's a YODA piece that the infrastructure team has, but there's also a lot of other pieces that need to get updated to be able to use this. And this is going to involve the JCSDA core team as well as contributors from partner organizations. So it's a pretty wide-reaching audience or developer audience that's going to be able to use this. So having this test bed in place is going to allow for development and testing in workflow environments similar to our partners' operational workflows. And that's going to help greatly facilitate getting us pointing in the right direction and developing this thing and with the targets in mind. So how much time do I have? Okay. All right, great. Yeah, I'll just wrap it up here. So methodology employing partner JEDI-Skylab configurations provides a rapid means for a new technology to be integrated into a target operational center workflow. This is due to these different configurations that we can put in this JEDI-Skylab testbed that emulate the real operational workflows. And also a consistent shared development infrastructure is provided. We have shared GitHub repositories, continuous integration, agile methodology, and we have this common software stack that spack-stack provides that's built on all the workstations, HPC platforms, and AWS EC2 instances. So you get the same environment on all these disparate platforms. And then these combine to enable rapid development of a new functionality, such as this continuous DA feature that's planned for the next year. So with that, that concludes my talk, and thank you for your attention, and we can do questions.
Thank you, Steve. Any questions? For the different Skylab customers, do you have different performance requirements? And if they can give you performance requirements, can you adapt to meet them by either limiting the ingest of data or maybe using more resources to meet their requirements? Let's say I want to forecast every 3 hours instead of 6 hours, or I only need it every 12 hours.
Yeah, that's very true. We do have these different performance requirements. A lot of the stuff that we do now is global forecasting, and we're starting to get into more regional applications and things like that. So that kind of requires setting up the boundaries of the region that you have. So it's kind of a different way to set up. But this thing that becomes maybe a different thing that you put in the EWOC workflow to bring in the boundary conditions, and then you have different settings for the forecast system to deal with that, but that's part of the EWOC workflow where you set up the configuration for the forecasting system. And there's that aspect of it. And there's also this aspect like what you mentioned, like we want to start doing forecasts at shorter intervals, which require, bringing in observation data faster, but that kind of is in alignment with that continuous DA thing, that the idea behind that is to just use more and more observations as they become available. So it can adapt to that as well. And also this highly collaborative environment that we have, if there's a new partner that comes online with a new system, it's relatively easy. It's not trivial, but it's relatively easy for them to get wired in and start using this system. And that's also true with academic organizations. And that's one of the big values I think that we see with this moving forward is this gets academic organizations more tied in with actual operational workflows. So we can handle, we'll be able to handle that as well. So maybe an example of that is the University of Oklahoma has all this expertise in radar, and they're like the severe storm center of the nation or whatever. And we've just recently completed a first round of getting radar data processing and assimilation into the system with the help of a professor at OU and a couple graduate students. And they were able to kind of take the system and learn it and get to the point where they could contribute. It happened relatively quickly, maybe over the course of a year and a half, they went from learning the system to contributing a assimilation capability.
Thanks.
Sure.
Any other questions? I can have one really quick. So not directly related to the main topic of your talk, Steve. You mentioned a tool called Terraform. Could you a bit elaborate on it? So is it really helpful for only the cases where you had to manage multiple repositories, or what was the use case? Maybe one more time.
So I'm not the expert on Terraform. That's one of the other people on the team. But from what I can gather, it's basically a thing that helps you configure GitHub. So any of the features in GitHub, I think you can automate with this. So I think it's not limited to the repositories. I think you can also do the actions and some of the other features that you have with it. But I'm not. It's difficult for me to speak to that because I'm not the expert.
Thanks so much. Any more questions? Okay, thank you so much, Steve.
All right, like Orhan mentioned, I'll just take the end of this session in terms of moderating, but we have one final talk from Alex Richert. I feel like we've alluded to this talk all day, so yeah, you get to take us home.
All right, wonderful. It's only if I figure out how the clicker works. All right, there we go. All right, good afternoon. I'm Alex Richert, and I'm going to talk about spack-stack, which is a software management framework that is built and maintained in collaboration between JCSDA, NOAA EMC, where I'm a contractor, and the NOAA Earth Prediction Innovation Center, NOAA EPIC. So just to give a quick overview, I'll talk about the motivation and history for spack-stack and its relation to SPAC, which is ultimately what it's based on. I'm going to do a kind of introduction for users. So if you are somebody who uses one of our target applications, then hopefully there'll be some useful information there. But I also want to give a flavor of kind of what the usage looks like for those of you who are developers who may not necessarily ever interface with spack-stack directly, but who may have your own package management needs and might benefit from seeing a little bit of the nuts and bolts of our approach. And then after that, I'll broaden the discussion more to kind of talking about aspects of spack-stack and SPAC that are useful for developers with package management needs, like using it for approaches for installing your own software dependencies and so on, and also what SPAC can do for you in a software development context, even if you don't strictly need to install or deploy large stacks with it. So the fundamental motivation for spack-stack is that modern weather forecasting workflows have a lot of software dependencies. They're increasingly complex, and I don't think that's going to, I don't think that trend is going to reverse anytime soon. So for example, the unified forecast system applications, those have, maybe around 20 direct dependencies each. So that's not including all the low-level libraries, or for that matter, even compilers or MPI libraries. These are just the libraries that get directly interfaced or called through the code. So the global workflow, including the operational GFS and GEFS applications, those have over a couple dozen direct dependencies, and the JEDI data assimilation suite has something like a whopping 94 direct dependencies. And if you add up all of the low-level dependencies you have to compile and so on, and all the ancillary stuff, you're probably talking about something like a couple hundred packages. So that's a lot to handle, needless to say. So as far as the question of how do you go about installing these dependencies, option one is manual installation. And from a NOAA EMC perspective, in kind of the bad old days, that's how things were done, is each developer would compile their own HDF5, their own NetCDF, their own ESMF, or maybe they would borrow one from a friend, which was based on the zlib of another friend. And so it, for one thing, results in a lot of ultimately unnecessary duplication of work. And it also just leads to this patchwork of inconsistent versions and build options across systems. And so it really just creates this kind of snowballing pile of both short and long-term risks, because when you start seeing, let's say, numerical differences between systems, you don't even know where to start with diagnosing that, because there's just so many possibilities as to where that can be coming from. So option two is automation, scripted up. And so the predecessor to spack-stack at NOAA EMC is a framework called HPC Stack, which is now basically retired. So there's a lot more consistency. So this, compared with manual installations, this was really a huge step forward, because now you get the same versions and basically the same build options, and so on across systems. You can still have inconsistencies because of compilers or different MPI flavors or what have you, but it was definitely a big step forward. Ultimately, though, building and maintaining it is hard work, and it ultimately consists of purpose-built scripts. So NetCDF has a script for building that. There's a separate script for building ESMF, and that's not bad. And you can kind of workload-wise, you can kind of muscle it out when you're dealing with maybe a couple dozen applications, but especially as the operational suite in the next 5+ years is going to move increasingly toward using JEDI for data assimilation, that really doesn't scale well, because at the end of the day, when you have twice as many packages to install and support, it means twice or more the work, and so on. So option three, and the current and future solution, is spack-stack. So with spack-stack, we retain those benefits of automating our configurations and deployments, but more of the work is done for us, because a lot of the under-the-hood functionality, as well as the coding for building the kind of package-specific build instructions, more of that is already done for us through SPAC, which I'll get into in a moment. And ultimately, it's just a more extensible and flexible framework. So from a kind of long-term support perspective, spack-stack really yields a lot of advantages. So before I can really get into what spack-stack is and what it does, I'll talk about SPAC. So SPAC is a package manager that is specifically built for scientific HPC workflows. The core development team is out of Lawrence Livermore National Lab, and it was basically invented as a response to the kind of repeated observations that probably many of us have experienced, of seeing grad students, postdocs, and so on just running into the same problems over and over, trying to build out software stacks, and especially the larger those stacks gets, and the the larger those stacks get and the more need that there is for self-consistency within those stacks, then, you know, installing things by hand is very often not a good option. SPAC has recipes for over 7,000 packages. I think it's actually closer to 8,000 now. So that's pretty much every scientific library you've just about ever heard of, and probably lots that you haven't. SPAC's defining feature is its use of a directed acyclic graph scheme for modeling the relationships between packages. So again, where SPAC really shines is if you need to build a large stack and you want to do it in a self-consistent way, where everything that uses HDF5 is going to use the same version, the same configuration, and so on of HDF5, and so on, the same MPI flavor and version, and so on. So SPAC uses those to model the dependencies. The constraints themselves are provided by the user, and then within the package recipes themselves. So as a kind of toy model here, let's say that I tell SPAC that I want to install NetCDF version 4.9.2, and I want to do so with MPI support. That's the constraint or the requirement that I provide to SPAC. SPAC provides its own constraints. Some of that is in the backend logic, and some of that is in the recipes themselves. So in the NetCDF recipe, it has an awareness that, okay, we're going to need HDF5 version 1.8.9 or later, and we need to have MPI support for having MPI support in NetCDF. And basically, SPAC takes all of those constraints from the user and from the SPAC code itself and runs those through basically a combinatoric solver, which then, and it applies kind of a series of preferences, like, you know, if you don't specify a package version, it'll generally default to the most recent, and so on, so that it will yield one single unambiguous installation plan, so that by the time you hit the installation button, you know exactly what it is that you're going to get in terms of versions and build options, and so on. And there's a fair bit of flexibility in terms of what, you know, the kind of degree to which you want to, you know, for example, have, you know, HDF5 have only one version and configuration for your whole stack, or if you want to build in some flexibility and so on. And so SPAC is also has the virtue of being pretty extensible and customizable. It's used in a whole range of use cases. It's especially popular in HPC these days. So there's a lot of built-in functionality that's really valuable in that regard. And that brings us to spack-stack. So spack-stack ultimately is a set of configurations and extensions for SPAC. So the quote unquote real heavy lifting in terms of the kind of the back-end code, the solver, the recipes, all that's provided for us through SPAC. So what spack-stack really does is it provides a set of site configurations for the HPC and cloud systems of interest, and then some extensions that I'll show off in a minute that kind of make kind of some convenience functionality. So again, spack-stack is a collaboration between JCSDA, NOAA EMC, and EPIC, and it serves our various applications. So that would namely be the JEDI suite, the UFS applications, and global workflow. So the spack-stack deployments are done as a unified environment. So for the few hundred packages that we end up installing on each system, with the exception of 2 of them, we basically have one version and one build configuration picked out that serves all of our various target applications. And we deploy that unified environment across 12 HPC systems, which you can see listed here, along with several cloud platforms. And then there are also releases of Docker and Singularity containers. We do our deployments quarterly and maintain them for a year, and we basically do that so that we're not forcing development teams to be constantly upgrading to the latest version of each package. So before I get into usage, just to kind of answer the general question of, you know, should I use spack-stack or should I use SPAC? I would say in general, if you work with one of these applications intended for support by spack-stack, so again, that's, you know, JEDI applications, UFS, global workflow, and so on, then you'll probably want spack-stack. Ideally, that'll be a you know, pre-built copy either on an HPC system or in a container, or you may choose to build it yourself, like on, you know, on your laptop or something like that. But for other users, I would generally recommend using SPAC because if you're not using those site configurations and some of the functionality more specific to how we apply our templates and so on, then you're not really going to benefit from spack-stack. So I would say for all other use cases, go with Spack. Spack is also quite well supported. They have their developers are pretty active on their Slack channel. So I would say if you need to sort of step things up in terms of how it is that you're obtaining your software, then Spack is very often a good way to go. All right, so as promised, a kind of introduction for users. So part one, this is kind of an overview of how users would go about using an existing HPC installation. So for the 12 systems that I mentioned, we have a list in our documentation of the paths of the directories on those systems, and then there are, in principle, a couple ways of using Spack environments. We use environment modules, so either Tickle or LMOD environment modules, depending on just whatever the sysadmins have installed on a given platform. So the access is basically just module use for the appropriate path. And then we use these meta modules, so the module load, stack, and then compiler name. So this could be, module load, stack Intel, and then stack, Intel MPI or what have you. So those are the access points to loading up the other individual packages, and then from there it's just the usual kind of module load for whatever your packages of interest are. Part two, using containers. This part's a little thinner because it's not a part that I'm as familiar with, but basically JCSDA and EPIC both publish containers. So some of those are, for instance, available on Docker Hub. So with a Docker pull, you can obtain those if you want to run spack-stack that way. And then the kind of third major category of use case would be users who want to build their own. So this would be either maybe needing to do some development work on one of the HPC systems and not using one of the existing stacks, or more likely installing it on a personal workstation or laptop and so on. So basically, you obtain the code. It's available through GitHub. The underlined elements here are the kind of spack-stack specific functionality. So we have our own script for setting up the environment so we can access these commands. And then the next line there, spack-stack create env, that's sort of our own convenience function for creating environments in a way that lets us directly access our configuration templates, the site configurations, and so on. And then the rest there, activating, solving, and installing the environment. That's all done through just the native SPAC commands. And then at the end there, once you've built the modules for the individual packages, then we have our own function for creating those the high-level meta modules for accessing the stacks on each system. So for getting support, we basically do everything through GitHub. So we pretty much try to do everything through issues on GitHub. Obviously, we're happy to have code contributions. So if you are interested in spack-stack, please feel free to check out our GitHub, and we'd love to have more contributors. And we do our documentation through Read the Docs, which the link is there on the screen. So before I talk about some more of the broader development use cases, I want to give kind of an overview of a kind of sort of pocket guide for choosing a package manager, because Spack, in some ways, it's kind of the big guns of package management, so it's not necessarily always the thing that you want to use. I won't go through all of these, but I think the main takeaway message here is that there's a kind of, as in so many things, there's a trade-off between the flexibility of the tool that you're using and the learning curve. So Spack would generally be considered, I think, at kind of one end of being ultra flexible and extensible, and you can almost always force it to do whatever it is that you want, and probably more so than if you're trying to install things through, let's say DNF or pip. But there's also going to be, depending on your use case, there may be more of a learning curve. Installations in Spack can be as simple as just saying, Spack install HDF5. But if your use case is that simple, then that's probably not, that you're probably not the sort of user who's going to want to use Spack anyway. The other observation that I would make about choosing a package manager is just from experience, it's usually best to choose one. We, initially on some of our systems, we had some Anaconda or Miniconda installed Pythons, and then we would sort of build the Python component of our stacks off of that. And that usually just ends up leading to more inconsistencies than it's worth. So I would say if you are basically operating within a Python ecosystem, then maybe using something like pip or conda, or maybe even your system's package manager if you're just using the kind of usual, NumPy, Matplotlib, SciPy kind of a stack. But then if you need more libraries outside of that, then probably Easy Build or Spack will be the way to go. And Spack does a pretty good job of handling like Python packages and so on. So Spack has a whole range of useful features. I'm just going to call out two of my favorites here. The spack develop command is really handy for basically allowing you to install modified code through Spack. So there's a number of use cases for this. So I could be a user who goes onto the HPC system. I load up the spack-stack installation, and then I say, oh, you know what? I really need to test this change to ESMF, or I'm getting a seg fault in such and such a package. So I want to test my own modifications to that package, but otherwise I want it to fall under the Spack framework. In particular, I want to be able to use that Spack recipe that already exists. I want things to be done in a self-consistent way. I want to build the downstream dependence readily based on my modified code. And so Spack develop is a command that basically creates a persistent directory structure that you can modify and while you iterate on your code. So I found that to be really useful, and I'll talk about, in a few minutes, I'll talk about how that's really useful in a CI context. My very favorite Spack feature is environment chaining. That's another one that's useful in a range of contexts. So environment chaining basically means that you have a stack installed, and then you say, hey, you know what? I want to install the latest version of, in my example here, ESMF. So what it does is it allows you to basically recycle the packages that already exist in that upstream installation. It doesn't copy them, so that way you're saving on disk space. It's basically just pointing kind of under the hood. Spack in its environments database is going to point to that upstream installation, and then it'll just automatically pull in whatever packages you use. But then if I tell Spack, hey, actually, I want to build ESMF 8.5.0 this time, it'll go ahead and recycle the ones that it can, but then the package that I want to change, along with any downstream dependence, will automatically be updated to whatever, based on whatever constraints I provide. So this is really useful from a developer standpoint, because again, you can get onto one of our supported platforms and you can test the latest version of, let's say, ESMF without having to rebuild the whole stack. So that's really handy, and it's also been really useful for our deployments, because we're trying to support a lot of applications at once, and inevitably with each release that we do, there's going to be one development team that says, hey, wait, this one version of this one package doesn't work for us. So instead of having to unroll and modify and re-roll our deployments, we can just add on one of these chained environments, change whatever set of packages we need to without having to rebuild everything. So it saves us time, and it also minimizes risk, because it minimizes the sort of inadvertent differences that could be introduced between stacks if we were to rebuild everything. So it's been a really nice tool for getting our different development teams on track for all converging on being able to use the one unified environment without further modifications. So some of the additional functionality that's provided specifically by spack-stack, some of this is stuff that I would say is generally useful for software deployments, but that Spack just happens to not include. So occasionally we'll run into issues of the Spack solver unexpectedly giving us duplicate packages, so that's something that we can detect and troubleshoot. We have some utilities that interface nicely with Spack's built-in parallel installation capabilities, and then we also have some kind of installation, verification, validation, like checking permissions and this sort of thing. So we have those utilities, which again are also not provided through the main Spack repository. So just to kind of review the advantages of spack-stack, I mean, again, the biggest advantage is automation. And, again, because we're using package recipes that are largely already written for us, yeah, maybe we have to develop them a bit, make updates once in a while, but ultimately it helps us scale up our work, because implementing twice the number of packages is going to be less than doing twice the work. We've gotten pretty adept at adding new site configurations, and that includes on cloud platforms. So that's been a real game changer, certainly for NOAA EMC, as far as letting developers get their applications into the cloud without having to build their own stacks and so on, or being able to do so quickly in any case. And again, I'll just reiterate how awesomely useful environment chaining is. Some of the challenges we've run into, I mean, consolidating configurations is hard. Having this unified environment that supports every application is difficult, but it's, I think we've shown it can be done. And then another challenge is that just because of kind of organizational requirements, constraints, and just kind of the history of how these things are done, we use that module interface, so we're doing module load for everything. That can be a bit restrictive in terms of, if we want to have multiple copies of a given package and so on. So that always throws a little bit of a wrench at us, but it's something we've managed to navigate, and there's potentially other alternatives available through SPAC. So bottom line on spack-stack, it's been really key to providing consistency across systems, minimizing risk, and saving developers time so that they can get to the good stuff of developing and deploying their models. So I want to speak a little bit more to general scientific developers now. So even if you're not necessarily interested in SPAC or spack-stack per se, I think that there are some ways in which SPAC can be relevant and useful to you. First, I want to advocate for SPAC as being a good way to distribute scientific software. On the right here is the results of a 2020 user survey. I mean, at this point, I would say SPAC is more or less the de facto standard in terms of building out stacks on HPC systems. There's a good chance that it's what your HPC sysadmins are using behind the scenes, but it's used across a range of government labs, university settings, and some in private industry. So it's a good way. There's a pretty good user base for it. So I think it's a good way to distribute software. The recipes that are provided in SPAC, so there's basically one file for each package that determines how to build it. I would say generally those work better when they are maintained by developers. So if you do, if there is a SPAC recipe for your package, or if you create one, I would urge you to maintain it, because it really makes things a lot smoother. There are also advantages to you in distributing through SPAC. The biggest one being that it can reduce some of the maintenance or kind of user engagement burden for you, so that instead of having to answer questions from people who don't know how to use CMake or this or that, you can just tell them to do SPAC install, and if that doesn't work, you can refer them to the SPAC Slack channel, where the developers are pretty active. So you can offset some of your user support burden that way. So yeah, again, I just want to ask that if you do write scientific software for others to use, please consider writing a SPAC recipe. Just as kind of an aside, if you do, SPAC has a fair bit of built-in awareness for a number of build systems. It does a pretty good job, for example, with Python packages. So if you're already distributing through PyPy pip, let's say, because you've got a setup.py or pyproject.toml or what have you, SPAC does those pretty readily, and often you don't really have to do a lot of your own sort of customizations or additions to the recipe. So that's usually a pretty straightforward process for that matter. And then, of course, just the other more general build tools, CMake, AutoTools, Meson. SPAC will pretty much handle whatever you throw at it. So if the way that you build your software is some, crazy convoluted system of shell scripts and whatever else, you can certainly do that through SPAC. But if you're considering, moving to one of these build systems, and you're also considering writing a SPAC recipe, I would suggest, as a matter of kind of order of operations, move to one of these build systems first, because you can probably make things that much smoother for you in developing and maintaining the recipe. So the last thing I want to talk about is the use of SPAC in continuous integration workflows. So there are a number of advantages to using it. So we use it on the NCEP libraries team, for example, at NOAA EMC. We use SPAC in our CI workflows to basically build the dependencies for a given library that we want to test, code modifications for in GitHub Actions, and then it's also a chance to test out our SPAC recipe. So building modified code is made easy in SPAC through that SPAC develop command that I mentioned. You just use that to point to the modified code that you check out in your workflow, and then it will apply the SPAC recipe and take care of the rest for you pretty readily. Build caching accelerates workflows. So of course you can't cache the code you're testing itself, but all of the dependencies can be cached. So especially if normally you're having to build or install, NPI or a whole bunch of dependencies each time, then that built-in functionality in SPAC couples really nicely with GitHub Actions or the other services ability to cache packages. SPAC can run your unit tests for you at install time. So in addition to testing our builds, we can also run make test, make check targets. You can customize that as much as you like in your recipe, but it's pretty straightforward to run unit tests. And then another nice aspect of it is that with no additional lines of code, when I point SPAC to my modified code, I can also point it to downstream dependencies and have those install through SPAC. So in addition to checking for bugs by making sure that those downstream dependents can still build, I can also have it run the unit tests for those packages. Again, I mean, of course, you can do that without SPAC, but you can do this with no additional lines of code, so it's pretty straightforward to implement. So you're essentially getting a lot of extra testing for free. So that's pretty cool. So bottom line here is on the NCEP libraries team, our combination of using CMake CTest, GitHub Actions, and SPAC really reduces the risk of months later discovering regressions because of some hiccup, some bug in a downstream code that we failed to account for when we initially merged the code. So to wrap up, spack-stack has been a game changer for, I think it's fair to say, all of the agencies in our collaboration, JCSDA, EMC, and EPIC. And it's been really valuable for both in HPC and cloud contexts, as well as for individual users on workstations and laptops. A lot of our future efforts, other than just kind of general maintenance and so on, will be further automation of our deployments. There's still a lot there that we're doing by hand, so I think that's something that we can make a lot of progress on. SPAC, again, really shines in situations where you want to build a large self-consistent software stack. Again, if you're just installing a few packages, then maybe you don't need to get out the big guns, but for some of these larger scientific workflows, weather forecasting workflows, then SPAC is a really valuable tool. And again, if you're a scientific software developer, please consider disseminating your software through SPAC, and especially if you're already doing so through pip and conda and so on, then it should be a pretty straightforward addition and not too much pain, not too much work to also release and maintain a recipe through SPAC. So I will stop there and take questions. Thanks so much.
All right, thanks, Alex. Any questions in the room? Looks like we do have one online. I'll read it for you, Paul. Maybe a typo, but a slide showed approximately 600 Conda packages, but Conda Forge alone has over 24K packages.
Okay, yeah, I think I left out Conda Forge in my numbers there, so apologies.
Yeah, and I know the general advice we have here at NCAR, at least, is to use Conda Forge and not the official repositories. So I think that's probably what people are more used to, at least here.
Okay.
A comment about the use of modules that I really didn't understand. I wanted to go back to that.
Okay.
Modules really, you can load and support multiple environments by using modules. And your comment seemed to be exactly the opposite of that. So could you elaborate?
Yeah, so I guess I was referring to more from a deployment perspective. We've kind of run into some it basically has to do with the fact that it follows the way that the internal logic of the module system works is based on the file system hierarchy. So if you have for example, we can't readily support like 2 copies of HDF5 within the same stack, because then we're going to have collisions between the names. So once something is deployed, then it's less of an issue, but it's difficult to well, again, to have, if you have a low-level library that has a bunch of downstream dependents, putting all of that in the same, having that all end up in the same sort of module file hierarchy has been tricky for us in the past, and that was sort of part of the move to the unified environment.
Maybe I'll ask a quick question. So I, as somebody who did this comparison before and came up with SPAC as the answer, when the team was moving from HPC stack to the next thing, was there a comparison done between SPAC and Easy Build and reasons for going with SPAC?
I don't know. That's a little bit before my time as far as the management decisions there. I don't know offhand if Easy Build was something that was specifically considered. I think it was, as I understand it, it was mainly down to whether to continue with HPC stack versus going to SPAC.
All right, any other questions in the audience or online? All right, well, thanks, Alex.
Thanks.
And that actually wraps us up for today. So thanks to everybody who participated and presented. So tomorrow we will start at the same time. Tomorrow is going to be a tutorial day. So there'll be a morning tutorial and a afternoon tutorial. And we'll still have, you know, the lunch and the breaks and all that. And then Wednesday and Thursday, we'll go back to some more talks. So yeah, I hope you get to get out and enjoy the Colorado weather before it gets a little windy tomorrow. And Tasia has another announcement, so I'm gonna.
Hi, thanks everybody. If you are in person, there's still some snacks. Feel free to take them home. Otherwise, they take them back. So I recommend just taking some home. Thank you.
Thank you. Yeah, perk of attending. So we'll see you all tomorrow. Thanks.